Please subscribe to support the channel. Look up into the night sky and try to imagine the distance to the stars you see twinkling above. Your mind cannot truly grasp it. The human brain, evolved to navigate forests and savannas, to judge the distance to the next tree or the far side of a valley, simply lacks the capacity to comprehend the true scale of space. This isn't a failure of imagination but a fundamental limitation of our cognition, and it's the first hint of why humanity's dreams of reaching other planets beyond our immediate cosmic neighborhood will forever remain exactly that, dreams. Let's start with something seemingly manageable. Mars, our neighboring planet, the target of countless science fiction stories and ambitious space agency proposals. When Mars and Earth are at their closest approach, they're separated by approximately 55 million kilometers. At their furthest, that distance balloons to over 400 million kilometers. These numbers are so large they become meaningless abstractions. To put it in perspective, if you could drive to Mars in a car traveling at highway speeds, never stopping, never slowing down, it would take you over 6,000 years to arrive. Even our fastest spacecraft, using gravity assists and optimal trajectories, take between 6 to 9 months to reach Mars. 9 months to reach our nearest planetary neighbor, a world so close we can see it with the naked eye as a bright dot in our evening sky. Now expand your thinking outward. The outer planets of our solar system, the gas giants Jupiter and Saturn, the ice giants Uranus and Neptune, are exponentially more distant. Neptune, the furthest planet from the Sun, orbits at an average distance of about 4.5 billion kilometers from our star. The Voyager probes, launched in 1977 and traveling at roughly 17 kilometers per second, took 12 years to reach Neptune. 12 years of continuous flight through space to reach a planet still within our own solar system, still gravitationally bound to our Sun, still part of our immediate cosmic neighborhood. But these distances, as staggering as they are, represent only the tiniest fraction of space. Our solar system exists in a bubble, a small pocket of relative proximity held together by our Sun's gravity. Beyond Neptune lies the Kuiper Belt, a region of icy bodies extending outward for billions more kilometers. Beyond that, the Oort cloud, a theoretical sphere of comets surrounding our solar system, reaching perhaps a light year from the Sun. A light year, remember, is the distance light travels in 1 year, moving at 300,000 kilometers per second. Light, the fastest thing in the universe, takes a full year to cross this distance. For a spacecraft like Voyager, traveling at a mere 17 kilometers per second, it would take approximately 18,000 years to traverse a single light year. And here's where the true tyranny of distance reveals itself. The nearest star to our Sun, Proxima Centauri, is 4.24 light years away. Using our current fastest spacecraft technology, a journey to Proxima Centauri would take over 70,000 years. 70,000 years of continuous flight through empty space just to reach our nearest stellar neighbor. To put this in historical context, 70,000 years ago, modern humans had only recently left Africa, had not yet developed agriculture, had not built the first permanent settlements, had not created writing or mathematics or any form of civilization as we know it. The entire span of recorded human history, from the first Sumerian cuneiform tablets to today, represents less than 1/10 of the time it would take to reach Proxima Centauri with our best current technology. The distances only grow more incomprehensible from there. Proxima Centauri may be our nearest neighbor, but it's an anomaly of proximity. Most stars are separated by far greater distances. The Milky Way galaxy, our home galaxy, contains between 200 and 400 billion stars spread across a disk approximately 100,000 light-years in diameter. Other galaxies exist millions and billions of light-years distant. The observable universe extends 46 billion light-years in every direction, containing an estimated 2 trillion galaxies. These numbers transcend human comprehension. They become abstract symbols on a page rather than distances our minds can meaningfully process. This incomprehensible scale creates a fundamental problem for space exploration that goes beyond mere engineering challenges. We're not talking about building a better rocket or developing a more efficient propulsion system. We're talking about distances so vast that they place practical limits on what's physically possible regardless of technological advancement. Even if we could somehow approach the speed of light, which we cannot, a journey to many exoplanets would still take years or decades from the perspective of those traveling, and much longer from the perspective of Earth due to relativistic effects we'll discuss later. The galaxy is not a small town where you can visit your neighbors. It's an ocean of darkness punctuated by islands of light separated by distances that mock our ambitions. Earth is not just our home, it's our prison, bounded not by walls we might break through with sufficient ingenuity, but by the fundamental structure of spacetime itself. We are trapped on this pale blue dot not by a lack of courage or insufficient funding for space programs, but by the architecture of the cosmos. Consider what this means in practical terms. When we send commands to a Mars rover, there's a communication delay of between 3 and 22 minutes depending on the planet's positions. This makes real-time control impossible. Rovers on Mars must be semi-autonomous, programmed to make decisions independently because by the time they receive instructions from Earth and send back confirmation, the situation may have changed. Now imagine trying to explore a planet orbiting Proxima Centauri. A radio signal traveling at light speed would take 4.24 years to reach the planet, and another 4.24 years for a response to return. Any question asked of astronauts there would receive an answer 8.5 years later. You couldn't guide their mission, couldn't help them solve problems, couldn't even have a conversation. They would be more isolated than any human has ever been, cast adrift in time as well as space. This is the first and most obvious barrier to interplanetary and interstellar travel. Space is unimaginably, incomprehensibly, prohibitively vast. But distance alone might be surmountable if we had the right technology. Perhaps we could develop suspended animation, putting astronauts to sleep for the duration of long journeys. Perhaps we could build generation ships where multiple generations would live and die en route to distant worlds. Perhaps advanced propulsion systems could achieve speeds far beyond what we currently manage. Before we can entertain such solutions, we must confront an even more fundamental problem: the mathematics of space travel itself, particularly a deceptively simple equation formulated over a century ago that places hard limits on what's achievable regardless of our technological sophistication. In 1897, a Russian scientist named Konstantin Tsiolkovsky was contemplating the problem of space travel decades before the first airplane took flight. He derived an equation that would become fundamental to astronautics, an equation so important it's now known simply as the rocket equation. The Tsiolkovsky rocket equation describes the relationship between the velocity change a rocket can achieve, the effective exhaust velocity of its propulsion system, and the ratio of its initial mass to its final mass. In simpler terms, it tells us how much fuel we need to go how fast. The equation appears deceptively straightforward. The change in velocity equals the exhaust velocity multiplied by the natural logarithm of the initial mass divided by the final mass. But this mathematical simplicity conceals a devastating practical reality. The logarithmic relationship means that as you want to go faster, the amount of fuel you need doesn't increase linearly but exponentially. Want to go twice as fast? You don't need twice as much fuel, you need exponentially more. Want to go 10 times faster? The fuel requirements become astronomical, often literally larger than is physically possible to construct. Here's why this creates an insurmountable problem. Every kilogram of fuel you add to your rocket has mass. That mass means you need more fuel to accelerate it. But that additional fuel also has mass, requiring still more fuel to accelerate it. This creates a recursive problem where the fuel requirements spiral upward exponentially. For trips within our solar system at relatively modest speeds, this is manageable, though barely. The Saturn V rocket that sent astronauts to the Moon weighed approximately 3,000 metric tons at launch. Of that mass, the actual payload that reached the Moon, the lunar module and command module, weighed only about 45 metric tons. In other words, roughly 98.5% of the rocket's mass at launch was fuel and structural components that would be discarded along the way. Only 1.5% was the actual spacecraft that completed the mission. Now consider what happens when we try to scale this up for more ambitious missions. Let's say we want to send a spacecraft to Proxima Centauri in a reasonable time frame. Perhaps we want to achieve 10% of the speed of light, which would make the journey take roughly 42 years. This is extraordinarily fast by current standards. Our fastest spacecraft, the Parker Solar Probe, reaches maximum speeds of about 0.064% of light speed during its close solar approaches. To achieve 10% of light speed would require accelerating to about 30,000 km per second. Using even the most optimistic assumptions about future propulsion technology, the fuel requirements become absurd. Even with a perfect fusion rocket, which we cannot currently build and which represents near the theoretical maximum of chemical to kinetic energy conversion, the mass ratio required would be enormous. For every kilogram of actual payload, you would need hundreds or thousands of kilograms of fuel. But remember, you also need to slow down when you arrive, which means you need to carry enough fuel not just to accelerate to 10% of light speed, but also to decelerate from that speed at your destination. This effectively doubles your fuel requirements, and since fuel has mass, it more than doubles them due to the recursive nature of the rocket equation. Let's work through a simplified example with actual numbers. Suppose we want to send a modest 10-ton payload to Proxima Centauri at 10% of light speed using a fusion rocket with an exhaust velocity of 10,000 km per second, which is optimistic but theoretically possible. To accelerate this payload to 30,000 km per second, the rocket equation tells us we need a mass ratio of about 20. This means our initial mass must be 20 times our final mass, so we need 200 tons at the start, 10 tons of payload and 190 tons of fuel. But we also need to decelerate. This means our payload isn't actually 10 tons, it's 10 tons plus all the fuel we need for deceleration. If we need 190 tons of fuel for the deceleration phase, our actual payload for the acceleration phase is 200 tons, meaning we need 4,000 tons of initial mass. We've just gone from 200 tons to 4,000 tons simply by accounting for the need to stop at our destination. And this assumes we don't need to accelerate and decelerate at any other points, that we have perfect efficiency, that we lose no fuel to boil off during the multi-decade journey, and that our fusion rocket works exactly as optimistically theorized. The real numbers are far worse. Most propulsion systems we can actually build have much lower exhaust velocities. Chemical rockets, like those that powered the Apollo missions, have exhaust velocities of only about 4 to 5 km per second. Using chemical rockets for interstellar travel would require mass ratios so large that the initial spacecraft would need to be larger than planets. Even ion drives, which are extremely efficient but produce tiny thrust, would require centuries to achieve the velocities needed for interstellar travel, and the mass ratios would still be prohibitive. Some have proposed using light sails, which require no onboard fuel, pushed by powerful lasers from Earth or the Sun's radiation pressure. This eliminates the rocket equation problem for acceleration, but creates other insurmountable issues we'll discuss later. For now, understand that you still need some way to decelerate at your destination, and light sails provide no good solution for that. You can't shine a laser from Earth to slow down a spacecraft 4 light years away. The beam would disperse long before reaching its target, and even if it didn't, you need the spacecraft to somehow turn its sail around while traveling at enormous velocity, which itself requires propulsion. Others suggest nuclear pulse propulsion, essentially exploding nuclear bombs behind a spacecraft and riding the shockwave. This was seriously studied under Project Orion in the 1950s and 1960s. The design theoretically could achieve a few % of light speed, but would require thousands of nuclear explosions, create massive radiation hazards, and still faces the deceleration problem. Moreover, it would violate numerous international treaties and would likely render the spacecraft's crew dead from radiation exposure long before reaching its destination. The rocket equation is not just an engineering challenge, it's a mathematical law that describes fundamental limits on what's possible. You cannot clever your way around it. You cannot engineer your way past it. You can improve your exhaust velocity, you can make your spacecraft lighter, you can accept higher mass ratios, but you cannot eliminate the exponential relationship between velocity and fuel requirements. This equation, first arrived over a century ago, remains one of the most fundamental barriers to space exploration, and it ensures that reaching high velocities requires energy expenditures that push against the boundaries of physical possibility. Even if we could somehow solve the rocket equation problem, even if we discovered some revolutionary propulsion system that bypassed these constraints, we would immediately crash into an even more fundamental barrier, the speed limit of the universe itself. This isn't a technological limitation or an engineering constraint. This is woven into the fabric of reality, described by Einstein's special relativity, confirmed by thousands of experiments, and absolutely inviolable by any conceivable technology. In 1905, Albert Einstein published his special theory of relativity, which revolutionized our understanding of space, time, and motion. Among its many profound implications, the most relevant for space travel is that nothing with mass can reach or exceed the speed of light in a vacuum. This isn't because we haven't built a strong enough engine. It's because the speed of light represents a fundamental boundary in the structure of space-time itself, and approaching it requires infinite energy. To understand why, we need to examine what happens as an object accelerates toward light speed. According to special relativity, as an object's velocity increases, its relativistic mass increases. This doesn't mean it gains atoms or molecules. Rather, its resistance to further acceleration increases. At everyday speeds, this effect is negligible. A car moving at 100 km per hour has a relativistic mass only infinitesimally larger than when at rest. But as velocities approach the speed of light, the effect becomes dominant. At 90% of light speed, an object's relativistic mass is about 2.3 times its rest mass. This means you need 2.3 times as much energy to accelerate it further than you would if it were at rest. At 99% of light speed, the relativistic mass is about 7 times the rest mass. At 99.9% of light speed, it's about 22 times the rest mass. At 99.99% of light speed, about 70 times. The closer you get to light speed, the more dramatic the increase. At 99.999999% of light speed, the relativistic mass is about 2,000 times the rest mass. This relationship is described by the Lorentz factor, which approaches infinity as velocity approaches light speed. What this means in practical terms is that as you get closer and closer to light speed, each additional increment of velocity requires more energy than all the energy you've already expended. You're fighting against the structure of spacetime itself, trying to accelerate something whose effective mass is becoming infinite. Actually reaching light speed would require infinite energy, which is impossible. The universe simply doesn't contain infinite energy, and even if it did, there would be no way to harness and apply it. Some people, when first learning about this, imagine that perhaps we just need to find the right form of energy, or the right propulsion mechanism. But this misunderstands the nature of the barrier. Einstein's equations don't care how you're trying to accelerate. Chemical rockets, ion drives, fusion engines, matter-antimatter annihilation, whatever exotic propulsion you might imagine, all are subject to the same relativistic limits. You could harness the entire energy output of a star, and you still could not accelerate a spacecraft with mass to light speed. The laws of physics don't permit it. Moreover, special relativity introduces other problems that compound as velocities increase. Time dilation means that clocks moving at high velocities run slower relative to stationary clocks. At 90% of light speed, time aboard a spacecraft passes at about 43.6% the rate it passes on Earth. A one-year journey for the crew would correspond to about 2.3 years on Earth. This might seem manageable or even beneficial, but as we'll explore later, it creates profound practical and philosophical problems for any mission. Length contraction means that distances in the direction of motion appear shortened from the perspective of a moving observer. At 90% of light speed, distances appear contracted to about 43.6% of their rest length. This might seem like it makes journeys shorter, and from the traveler's perspective, it does. But from Earth's perspective, the journey still takes the full time dictated by the actual distance and the spacecraft's velocity. The crew might experience a shorter journey, but Earth would still wait decades or centuries for their return, and the travelers would arrive in what is, to them, the distant future. There's also the problem of energy to mass conversion. As you pump energy into accelerating a spacecraft, that energy itself contributes to the system's relativistic mass. You're not just fighting against the mass of the ship, you're fighting against the mass equivalence of all the kinetic energy it's acquiring. This creates another recursive problem similar to the rocket equation. The energy you add makes the ship harder to accelerate, requiring more energy, which makes it harder to accelerate, requiring more energy, in an escalating spiral that asymptotically approaches but never reaches light speed. Some have speculated about exotic solutions like warp drives, which theoretically would compress spacetime in front of a ship and expand it behind, allowing faster-than-light travel without actually accelerating to light speed locally. These concepts, most notably the Alcubierre drive, are fascinating thought experiments but face their own insurmountable problems. They require exotic matter with negative mass energy, which has never been observed and may not exist. They would require energy scales comparable to the mass energy of Jupiter just to transport a small spacecraft. They may be forbidden by quantum effects that make traversable wormholes unstable. And they may violate causality, allowing time travel to the past and all the paradoxes that entails, which suggests they're probably impossible. The speed of light limit isn't just a challenge to overcome, it's a fundamental feature of the universe we inhabit. Asking how we can travel faster than light is like asking how we can make a circle with corners or create a married bachelor. The question itself contains a contradiction. Light speed isn't fast. From the universe's perspective, it's the only speed. Everything moves through spacetime at light speed. Massive objects just trade their motion through space for motion through time. This is why time slows down as you accelerate. You're redirecting your motion through spacetime from the time dimension toward the space dimensions, but the total magnitude remains constant at light speed. What all of this means for space travel is brutally simple. We are fundamentally limited in how fast we can move through space. Even with perfect efficiency, even with unlimited resources, even with technologies we can barely imagine, we cannot approach anywhere near the speed necessary to make interstellar travel practical. A civilization thousands or millions of years more advanced than ours would face the same limits we do. This isn't a temporary obstacle waiting for sufficient technological progress. This is a permanent feature of the universe we inhabit, and it places absolute bounds on our ability to reach other star systems within reasonable timeframes. But let's suppose, for the sake of argument, that we somehow found a way around these limits. Imagine we discovered some exotic propulsion system that could safely accelerate a spacecraft to a significant fraction of light speed without running afoul of the rocket equation or relativistic effects. Even then, we would face another crushing reality. The sheer amount of energy required is beyond anything human civilization can realistically generate or store. To accelerate even a small spacecraft to a meaningful fraction of light speed requires energy expenditures that dwarf our current capabilities. Let's work through the numbers to understand just how impossible this is. Consider a relatively small spacecraft with a mass of 1,000 kilograms, about the size of a large satellite. We want to accelerate it to 10% of the speed of light, or 30,000 kilometers per second. The kinetic energy of an object is 1/2 times its mass times its velocity squared. For our spacecraft, that's 1/2 times 1,000 kilograms times 30 million meters per second squared, which equals approximately 4.5 times 10 to the power of 17 joules, or 450 petajoules. To put this in perspective, the entire annual energy consumption of human civilization is approximately 580 exajoules, or 580 million petajoules. Our modest spacecraft requires about 0.078% of all energy used by humanity in an entire year just for the acceleration phase. And remember, we need to decelerate too, effectively doubling this requirement. So we're looking at roughly 0.156% of human civilization's annual energy output to send one small spacecraft to 10% of light speed. Now consider that 10% of light speed would still take over 40 years to reach Proxima Centauri. What if we wanted to go faster, to make the journey in a more reasonable timeframe? To achieve 50% of light speed, which would reduce the journey to about 8.5 years, we need 25 times as much energy, assuming non-relativistic calculations. With relativistic corrections, the requirements are even higher. We're now talking about several percent of humanity's entire annual energy output for a single small spacecraft. And this assumes perfect efficiency, which is physically impossible. No energy conversion process is 100% efficient. Thermodynamics guarantees that some energy is always lost as heat. Real propulsion systems might be 10% efficient, or 20% if we're extraordinarily lucky with advanced technology. This means we need to generate 10 to 5 times more energy than these calculations suggest, just to account for inefficiency. Suddenly, we're talking about energy requirements that approach or exceed the entire annual energy output of human civilization for a single spacecraft carrying perhaps a few tons of payload. Where would this energy come from? Our current energy sources are laughably inadequate. The largest nuclear power plant in the world, the Kashiwazaki Kariwa plant in Japan, generates about 8,000 megawatts, or 8 times 10 to the power of 9 watts. Running continuously for an entire year, it produces about 2.5 times 10 to the power of 17 joules. This means even this massive installation would need to run for nearly 2 years at full capacity to generate enough energy for our single small spacecraft's acceleration, assuming perfect energy storage and transfer efficiency. In reality, you need it to run for a decade or more to account for losses. Solar power is even more inadequate. The sun delivers approximately 1,370 watts per square meter to the top of Earth's atmosphere. To collect 450 petajoules, you need to capture all the solar energy falling on about 10,000 square kilometers for an entire year, again assuming perfect collection efficiency. This is an array larger than the entire state of Connecticut, positioned in space with no atmospheric interference, operating continuously, somehow storing all this energy for later use, then transferring it to a spacecraft efficiently enough to be useful. The engineering challenges are fantastical. What about nuclear energy? The complete conversion of matter to energy via matter-antimatter annihilation represents the theoretical maximum energy density. Einstein's famous equation E equals mc squared tells us that mass and energy are equivalent, with the conversion factor being the speed of light squared. 1 kilogram of matter, completely converted to energy, yields approximately 9 times 10 to the power of 16 joules. So to get our 450 petajoules, we need to completely annihilate about 5 kilograms of matter-antimatter pairs. 5 kilograms doesn't sound like much, until you consider that we've never produced more than nanograms of antimatter. That containing antimatter is extraordinarily difficult since it annihilates instantly upon contact with normal matter, that producing antimatter is phenomenally expensive and energy-intensive, and that even if we could produce and store it, using it as propulsion requires somehow directing the resulting gamma rays and particle spray in a specific direction for thrust, which is perhaps impossible. The largest antimatter production facility at CERN produces about 1/1000th of a gram of antiprotons per year. At this rate, producing 5 kilograms of antimatter would take roughly 5 billion years, longer than the current age of the Earth. Some proposals suggest harvesting antimatter from natural sources, like the Van Allen belts where small amounts are created by cosmic ray interactions, or perhaps from regions near black holes or neutron stars. But the quantities available naturally are minuscule, the collection mechanisms are purely theoretical, and transporting antimatter safely is a nightmare scenario. A single containment failure would result in instant annihilation, releasing energy equivalent to a nuclear weapon. Even if we solve the energy generation problem, we face the storage problem. Batteries and chemical energy storage are woefully inadequate for the energy densities required. The best lithium-ion batteries store about 1 megajoule per kilogram. To store 450 petajoules would require 450 million kilograms of batteries, or 450,000 metric tons. This is 9,000 times more than our spacecraft's mass, making the entire enterprise nonsensical. We need to accelerate the batteries too, requiring even more energy in a recursive nightmare. Nuclear fuel is better but still inadequate. Uranium-235 produces about 80 trillion joules per kilogram through fission, meaning we need about 5,600 kilograms of uranium to generate our required energy, assuming perfect conversion efficiency. Add in the mass of the reactor, shielding, cooling systems, and fuel handling equipment, and you're looking at hundreds of tons. And nuclear fission produces thrust very inefficiently. Most of the energy is released as heat that must be radiated away rather than converted to directed kinetic energy. The fundamental problem is that energy density and power density are different things. Even if you could store enough total energy in a compact form, you need to release and utilize it at tremendous rates to accelerate a spacecraft. The power requirements, energy per unit time, are just as challenging as the total energy requirements. Accelerating gradually over years rather than months reduces power requirements but extends mission duration, increases radiation exposure, extends life support needs, and multiplies equipment failure risks. This energy problem becomes even more absurd when we consider not just one small probe but a crewed mission with life support, consumables, radiation shielding, and all the equipment humans need to survive. A crewed spacecraft would mass not 1,000 kilograms but thousands of tons. The energy requirements scale linearly with mass, so a 10,000-ton spacecraft needs 10,000 times as much energy. We're now talking about energy requirements that exceed the total energy output of human civilization over multiple years or decades. There's also the problem of waste heat. All this energy conversion produces heat, which must be radiated away. In space, the only way to shed heat is through thermal radiation, which is relatively inefficient. The spacecraft's radiators would need to be enormous, adding even more mass to the system. During high-power acceleration, the heat generated might exceed the ability of any reasonable radiator system to dissipate it, causing equipment to overheat and fail. The energy problem isn't just daunting, it's fundamentally prohibitive. We're not talking about building bigger power plants or developing better batteries. We're talking about energy requirements that approach the output of entire civilizations or even stars. To accelerate a spacecraft to relativistic velocities requires energy scales that are simply not available to us, nor will they become available through any foreseeable technological advancement. We would need to be able to harness the entire energy output of our sun for years or decades, which is so far beyond our current capabilities that it might as well be magic. This stark reality leads us to yet another crushing consequence of high-velocity space travel: time dilation. While this might initially seem like a benefit, allowing astronauts to experience shorter journey times, it creates practical problems that make interstellar missions fundamentally unworkable. Even if we solved every other problem, the distance, the energy, the propulsion, time dilation would create social, psychological, and practical barriers that render such missions pointless or impossible. Time dilation is a consequence of Einstein's special relativity that has been experimentally verified countless times. Moving clocks run slow relative to stationary clocks. At everyday speeds, this effect is negligible, but at high velocities, it becomes dramatic. The degree of time dilation is determined by the Lorentz factor, which depends on the ratio of the object's velocity to the speed of light. Let's examine a hypothetical mission to Proxima Centauri to see how this plays out. Suppose we've solved all the energy and propulsion problems and can accelerate a spacecraft to 90% of the speed of light. At this velocity, the Lorentz factor is about 2.3, meaning time aboard the spacecraft passes at about 43.6% the rate it passes on Earth. The journey to Proxima Centauri, 4.24 light-years distant, would take about 4.7 years from Earth's perspective. For the crew, experiencing time dilation, it would feel like only about 2.0 years of travel time. This might sound wonderful. The crew ages only 2 years while covering a distance that would take millennia at conventional speeds. But consider what this means. When they arrive at Proxima Centauri, nearly 5 years have passed on Earth. If they explore for a year from their perspective, about 2.3 years of Earth time, and then return, another 4.7 years pass on Earth. By the time they return home, over 12 years have passed on Earth while they've experienced only about 5 years of subjective time. They return to find that their children are 7 years older than when they left, aging past them. Friends have moved on with their lives, relationships have dissolved, technology has advanced. They're strangers in their own world, time travelers who went away and came back to a future they didn't participate in creating. This would be psychologically devastating, creating profound feelings of disconnection and loss. Now consider a more distant destination. The nearest potentially habitable exoplanet, Proxima Centauri b, is still only 4.24 light-years away. Most potentially habitable exoplanets we've discovered are tens or hundreds of light-years distant. A journey to a planet 40 light-years away at 90% light speed would take about 44 years from Earth's perspective. The crew would experience about 19 years. They would return to Earth having aged 19 years, but Earth would have aged 88 years. Everyone they knew would be elderly or dead. The world would be completely transformed. There would be fossils, people from a bygone era trying to integrate into a society that has evolved beyond their understanding. At even higher velocities, the disconnect becomes more extreme. At 99% of light speed, the Lorentz factor is about 7. A 40 light-year journey would take about 40 years from Earth's perspective but only about 5.7 years for the crew. They return to find that 80 years have passed on Earth. They left in 2025 and returned to 2105, having personally experienced less than a dozen years. Their society, culture, technology, everything has transformed. They are refugees from the past, isolated by time rather than space. This creates a fundamental question: what's the point of such a mission? If the goal is scientific knowledge, why send humans when the time dilation ensures they'll be disconnected from the civilization that sent them? Any data they collect could be transmitted back at light speed, arriving years before they do. If they discover something important and need advice or additional resources, communication delays measured in decades make such assistance impossible. They're fundamentally on their own, marooned in time. The ethical questions are also profound. Is it moral to send people on missions knowing they'll return to find their loved ones aged or dead, their world transformed beyond recognition? Can anyone truly consent to such a mission, knowing its full implications? How do you maintain mission motivation when crew members know that success means permanent exile from everyone and everything they knew? There's also the institutional problem. The space agency or government that launches such a mission might not exist when it returns. Priorities change, funding dries up, civilizations rise and fall. A mission launched in 1945 would be returning to a world that has experienced the Cold War, the space age, the information revolution, the internet, and the AI era. The institutions that launched it would be transformed or gone. Would anyone even remember to watch for its return? Would anyone care about its findings? Time dilation also creates paradoxes for communication. Radio signals travel at light speed, experiencing no time dilation. A message sent from Earth to a spacecraft traveling at 90% of light speed would appear blue-shifted and sped up from the spacecraft's perspective, while messages from the spacecraft would appear red-shifted and slowed down to Earth. This creates asymmetries in communication that complicate coordination and make real-time collaboration impossible. Furthermore, time dilation means that any navigation errors compound differently for the crew and Earth. If a spacecraft misses its target, the correction time experienced by the crew might be months, but years pass on Earth. Mission Control will need to accept that by the time they receive any data about a problem, the situation may have changed or resolved itself. The crew would be truly alone, unable to rely on Earth for guidance or assistance in any meaningful time frame. The psychological impact of time dilation can't be overstated. Humans are social creatures, connected to our communities through shared experiences and temporality. Violating this connection by having the crew age at a different rate than humanity creates a fundamental isolation that goes beyond mere physical distance. They would be aware, every moment of their journey, that with each passing day for them, multiple days pass for everyone they've left behind. This knowledge would be psychologically corrosive, creating anxiety and grief that no amount of training could fully prepare someone for. Some have proposed solutions like sending entire communities, so people age together and maintain social connections. But this just moves the problem. The community becomes isolated from humanity as a whole, creating a breakaway civilization that can never truly return home. After a few generations, they would be so disconnected from Earth culture that they'd essentially be aliens, humans who've evolved separately in their closed environment. Time dilation transforms space travel from a journey across distance into a journey across time, and in doing so, makes the entire enterprise practically and philosophically untenable. Even if we could physically accomplish such missions, the temporal disconnection they create undermines their purpose and viability. But let's set aside these temporal concerns and focus on the physical environment the crew would face during their journey. Space is not an empty void but rather filled with deadly radiation that poses an insurmountable threat to any human traveling beyond Earth's protective magnetic field for extended periods. This radiation is not merely dangerous, it's fundamentally incompatible with human biology in ways that cannot be engineered away. Space is permeated by cosmic rays, high-energy particles accelerated to near light speed by supernovae, neutron stars, black holes, and other violent cosmic events. These particles, primarily protons but also heavier atomic nuclei, carry tremendous energy. When they strike matter, they create cascades of secondary particles, penetrating deep into whatever they hit and causing widespread damage at the atomic level. On Earth, we're protected from cosmic rays by our atmosphere, which is thick enough that most cosmic rays collide with air molecules and create particle showers that dissipate their energy before reaching the ground. We're also protected by Earth's magnetic field, which deflects many charged particles away from our planet entirely. Even on the International Space Station, orbiting just 400 kilometers above Earth's surface, astronauts are still partially protected by the planet's magnetic field and receive radiation doses that, while elevated compared to ground level, are manageable for 6-month missions. Beyond Earth's protective envelope, the situation transforms dramatically. In deep space, there is no magnetic field to deflect particles and no atmosphere to absorb them. A spacecraft and its crew are exposed to the full fury of cosmic radiation. Studies have estimated that astronauts on a journey to Mars would receive radiation doses hundreds of times higher than they would on Earth, and Mars missions would last only months. For interstellar journeys lasting years or decades, the cumulative radiation exposure would be catastrophic. The biological effects of cosmic radiation are multifaceted and devastating. At the cellular level, high-energy particles damage DNA, creating mutations that can lead to cancer. Unlike the lower-energy radiation from X-rays or gamma rays, cosmic rays have such high energy that a single particle can traverse an entire cell, creating a track of damage along its path. This makes cosmic radiation particularly effective at causing double-strand breaks in DNA, which are difficult for cells to repair and often lead to cell death or cancerous mutations. Studies on astronauts who've spent time on the International Space Station show measurable increases in cancer risk even with partial magnetic field protection. NASA estimates that astronauts on a Mars mission would face a 5% increase in their lifetime cancer risk, and that's for a relatively short mission of 2 to 3 years. For an interstellar journey lasting decades, the cancer risk would approach certainty. Every crew member would develop multiple cancers during the voyage, and without sophisticated medical facilities and interventions, these cancers would be fatal. But cancer is actually the slower, more forgiving problem. Cosmic radiation also causes acute damage to the central nervous system. Studies on mice exposed to cosmic ray simulations show significant cognitive impairment, including memory loss, decreased spatial learning, and behavioral changes. The high-energy particles damage neurons directly and create inflammation in brain tissue that persists long after exposure. Extrapolating these results to humans suggests that astronauts on long-duration deep space missions would experience progressive cognitive decline, essentially developing radiation-induced dementia. This cognitive impairment creates a cascading failure scenario. As crew members lose cognitive function, their ability to maintain complex spacecraft systems, make critical decisions, and respond to emergencies diminishes. Mistakes become more frequent, response times slow, judgment deteriorates. In an environment where a single error can be catastrophic, this cognitive degradation transforms the crew from the mission's greatest asset into a liability. The radiation exposure also affects other organ systems. The cardiovascular system is particularly vulnerable, with radiation accelerating atherosclerosis and increasing heart disease risk. The immune system becomes compromised, making crew members more susceptible to infections. The gastrointestinal system can be damaged, leading to chronic digestive problems. The eyes are vulnerable, with cosmic radiation accelerating cataract formation and potentially causing other vision problems that would be impossible to treat adequately in space. The obvious solution seems to be shielding. If radiation is the problem, why not simply build thicker walls on the spacecraft? This is where we encounter another fundamental barrier. Effective radiation shielding against cosmic rays requires enormous mass, which brings us back to the rocket equation problem. Moreover, shielding can actually make some radiation problems worse. For lower energy radiation, conventional shielding materials like aluminum or steel work reasonably well. But cosmic rays are so energetic that when they strike shielding material, they create secondary particle showers that can be even more dangerous than the original particle. This is called secondary radiation, and it's a major concern for spacecraft design. Using heavy materials like lead, which works well for shielding against X-rays and gamma rays, actually makes the cosmic ray problem worse by creating more secondary particles. The best shielding materials are those with light elements, particularly hydrogen. Water, plastics, and other hydrogenous materials are more effective at stopping cosmic rays than metals. But even with optimal materials, the amount of shielding needed to reduce radiation to safe levels is enormous. Calculations suggest that to reduce cosmic radiation exposure to levels comparable to Earth's background radiation would require water shielding several meters thick surrounding all habitable spaces. Let's quantify this. Water has a density of 1,000 kilograms per cubic meter. A small habitable module 10 meters long and 4 meters in diameter has a surface area of about 140 square meters. Surrounding this with 3 meters of water shielding means adding approximately 420 cubic meters of water, which is 420,000 kilograms or 420 metric tons. This is just for shielding one small module, and it's the minimum required for adequate protection. For a spacecraft designed for decades in deep space with multiple habitat modules, life support systems, propulsion, fuel, supplies, and other equipment, the total mass with adequate radiation shielding would be tens of thousands of tons. We're back to the rocket equation problem. Accelerating this massive spacecraft to any significant velocity requires energy expenditures that are completely impractical. You're forced to choose between adequate radiation protection and a mission that's physically possible to launch. Some proposals suggest using electromagnetic fields to deflect charged particles, creating an artificial magnetosphere around the spacecraft. While theoretically possible, the engineering challenges are immense. The magnetic fields would need to be extremely strong and extend far from the spacecraft to be effective. Generating such fields requires enormous amounts of electrical power, which means large power plants, which means more mass. The superconducting magnets needed to create these fields would be massive, fragile, and require cooling to cryogenic temperatures, adding yet more mass and complexity. Moreover, electromagnetic shielding only works against charged particles. Neutrons and gamma rays, which are also components of space radiation, are unaffected by magnetic fields and would require conventional mass shielding. You can't eliminate the need for physical shielding, you can only hope to reduce it somewhat. There's also the problem of solar particle events. Occasionally, the sun releases enormous bursts of radiation in the form of coronal mass ejections and solar flares. These events can increase radiation levels by factors of hundreds or thousands for hours or days. On Earth, we're protected by our atmosphere and magnetic field. In space, a major solar particle event could deliver a lethal radiation dose in hours if astronauts are caught without adequate shielding. For missions within our solar system, spacecraft can carry a storm shelter, a heavily shielded area where crew can retreat during solar particle events. But this is only practical because such events are relatively short-lived. For an interstellar mission, you cannot predict when solar particle events will occur at any star systems you pass near, and you need full-time shielding rather than temporary protection. The radiation problem is not merely an engineering challenge, but a fundamental barrier that makes long-duration deep space travel incompatible with human biology. We evolved under Earth's protective blanket of atmosphere and magnetosphere, and our biology is simply not designed to function in the radiation environment of deep space. We can protect against it, but only by making spacecraft so massive that they become impractical to propel, creating an unsolvable conflict between safety and feasibility. Even if we somehow solved the radiation problem, perhaps by accepting higher cancer risks or developing radical new shielding technologies, we would face another deadly threat from space itself, the problem of impacts with micrometeorites and space debris. At the velocities required for interstellar travel, even microscopic particles become devastating weapons capable of destroying a spacecraft instantly. Space is not perfectly empty. Even in the vast regions between stars, there exists an incredibly diffuse medium of gas and dust particles. The interstellar medium has an average density of about 1 atom per cubic centimeter, with occasional denser molecular clouds reaching 1,000 atoms per cubic centimeter. This sounds incredibly sparse. Earth's atmosphere at sea level contains about 10 to the power of 19 molecules per cubic centimeter, but at high velocities, even these tenuous atoms become hazards. The kinetic energy of an object is 1/2 times mass times velocity squared. This means that kinetic energy increases with the square of velocity. Double your speed and you quadruple the energy of any collision. At interstellar velocities, this relationship creates catastrophic collision energies. Consider a spacecraft traveling at 10% of the speed of light, 30,000 kilometers per second. A grain of sand with a mass of 1 milligram striking this spacecraft would have a kinetic energy of approximately 450 million joules, equivalent to about 100 kilograms of TNT exploding on impact. A single grain of sand, something you could barely see, becomes a bomb. Even a dust particle with a mass of 1 microgram would have kinetic energy of 450,000 joules, equivalent to a bullet from a high-powered rifle. At these velocities, the spacecraft is essentially flying through a minefield where the mines are invisible and unpredictable. The damage from such impacts goes beyond simple penetration. At these extreme velocities, impacts create plasma. When the projectile strikes the hull, both the projectile and part of the hull are instantly vaporized and ionized, creating an expanding cloud of superheated plasma that can penetrate much deeper than the projectile itself. This plasma expands outward in a shock wave, potentially damaging systems far from the initial impact point. Electronic components are particularly vulnerable to these plasma bursts, which can induce electrical currents that fry delicate circuits. Shielding against hypervelocity impacts is extraordinarily difficult. Conventional armor, which works by absorbing energy through deformation, is largely ineffective because the impact energies are so high that any practical thickness of armor is simply vaporized. Whipple shields, which use multiple layers separated by gaps to fragment and dissipate incoming particles, work for lower velocities but become less effective as velocities increase. At 10% of light speed, you would need Whipple shields meters thick, adding enormous mass to the spacecraft. Some proposals suggest using sacrificial shields, thin layers of material placed far in front of the spacecraft to intercept and vaporize incoming particles before they reach critical systems. The idea is that the debris cloud from the vaporized particle and shield would spread out and hit the spacecraft as a more diffuse impact rather than a concentrated one. But this only works for small particles. Larger objects would punch through sacrificial shields and still impact the main spacecraft with devastating effect. There's also the problem of detection and evasion. At 10% of light speed, the spacecraft covers 30,000 kilometers every second. Even if you could detect an object in your path, you would have only fractions of a second to react before impact. There's no practical way to detect centimeter-scale objects at distances great enough to allow evasion, and even if you could, the energy required to change course at these velocities would be prohibitive. The density of the interstellar medium varies. In the general interstellar medium, impacts might be relatively rare, but passing through or near molecular clouds would dramatically increase the risk. These clouds can be light years across, and there's no way to map their exact distribution before a mission. The spacecraft might spend years traveling through safe regions, then encounter a dense cloud and be destroyed by multiple impacts before it can alter course. Larger objects are an even greater threat. While rare, the interstellar medium contains not just atoms and molecules but also dust grains, pebbles, and even larger bodies. A collision with a grain of dust a millimeter across at 10% of light speed would release energy equivalent to several kilograms of high explosive. A pebble 1 centimeter across would release energy equivalent to several tons of TNT. Any such impact would likely destroy the spacecraft instantly and completely. The probability of such impacts is difficult to calculate precisely because we don't have detailed maps of the interstellar medium along potential travel routes. But statistical estimates suggest that a spacecraft traveling to even the nearest stars would have a non-negligible probability of encountering dangerous particles. The faster you travel, the more devastating each impact and the higher the probability of encountering particles that can destroy your spacecraft. This creates another impossible trade-off. To make interstellar travel practical, you need high velocities to reduce journey times. But higher velocities make impact damage worse and require more shielding. More shielding means more mass, which requires more energy to accelerate, bringing us back to the rocket equation. You can't avoid the problem by going slower because then journey times extend to centuries or millennia, creating all the other problems we've discussed. Some have proposed using magnetic or electric fields to deflect charged particles before they impact. While this might work for individual atoms and ions, it's ineffective against neutral particles, dust grains, or anything with significant mass. The forces required to deflect even a small dust grain traveling at these relative velocities would be enormous, requiring magnetic fields so strong and extended that generating them would demand impractical amounts of power. Another proposal involves using lasers or particle beams to vaporize incoming objects before they reach the spacecraft. But detecting objects small enough and far enough in advance is nearly impossible with any foreseeable sensor technology. Even if you could detect them, you need to track potentially thousands of objects simultaneously and vaporize them all with perfect accuracy. A single missed detection results in catastrophic impact. The power requirements for such a system would be staggering, and the system itself would add significant mass and complexity to the spacecraft. The micrometeorite problem represents another fundamental barrier to high-velocity space travel. Unlike radiation, which can theoretically be shielded against with sufficient mass, or propulsion, which might theoretically be solved with exotic technologies, the impact problem has no good solutions. Physics dictates that high-velocity collisions release enormous energy, and there's no way to make a spacecraft both light enough to accelerate to high velocities and robust enough to survive the impact environment at those velocities. This brings us to perhaps the most mundane, but equally insurmountable challenge: keeping humans alive for the duration of an interstellar journey. The life support requirements for missions lasting decades or centuries are not merely difficult but approach impossibility when examined in detail. Every system must work perfectly for the entire duration, and the slightest inefficiency compounds over time into mission-ending failure. Human beings require several things to survive: breathable air with the right composition of oxygen and nitrogen, water for drinking and hygiene, food for nutrition, appropriate temperature and pressure, waste processing, and various environmental controls. On Earth, these needs are provided by the planetary ecosystem with minimal intervention. In space, every molecule of oxygen, every drop of water, and every calorie of food must be carefully managed in a closed-loop system with no margin for error. Let's start with oxygen. A human being at rest consumes approximately 550 liters of oxygen per day, or about 700 grams. This oxygen must be continuously replenished, either by carrying it, generating it through chemical processes, or recycling it from carbon dioxide exhaled by the crew. Carrying enough oxygen for a multi-decade voyage is impractical due to mass constraints. A single person needs about 250 kilograms of oxygen per year, so a 10-person crew on a 40-year journey would require 100,000 kilograms of oxygen, 100 metric tons. This doesn't include oxygen lost through leakage or consumed by chemical processes. The alternative is recycling systems. The International Space Station uses an oxygen generation system that electrolyzes water to produce oxygen, and a carbon dioxide scrubbing system that captures CO2 from the cabin air. Some of this CO2 is reduced back to water and oxygen through the Sabatier process, which reacts CO2 with hydrogen to produce water and methane. This system has an efficiency of perhaps 90%, meaning 10% of oxygen is lost and must be replenished from stored reserves. A 10% loss rate might seem manageable, but over decades it becomes catastrophic. After 1 year, you've lost 10% of your oxygen. After 10 years, assuming you're continuously replenishing from reserves, you've lost much of your reserve supply. For a 40-year mission, even a 1% annual loss rate would deplete reserves. There's no room for equipment failures, no tolerance for efficiency degradation over time, no margin for unexpected losses. Water presents similar challenges. Humans require about 3 liters of water per day for drinking, plus additional water for hygiene, food preparation, and equipment cooling. The ISS recycles about 93% of water, but achieving this efficiency requires complex equipment that constantly needs maintenance. Over decades, filters clog, membranes degrade, and pumps wear out. The recycling efficiency gradually decreases, and the water losses accumulate. Food is even more problematic. Currently, all food for space missions is launched from Earth. Freeze-dried, vacuum-sealed, and carefully packaged, it can last years but not decades. For a long-duration mission, you would need either to carry all food for the entire journey, which is prohibitive in terms of mass, or to grow food aboard the spacecraft, which presents enormous challenges. Growing food in space requires light, water, nutrients, controlled atmosphere, and space for cultivation. Plants need substantial light for photosynthesis, which means either large windows to collect sunlight, adding structural mass and creating radiation entry points, or artificial lighting, which requires enormous amounts of electrical power. Plants also transpire water, which must be captured and recycled, and they need nutrients that must be carefully balanced and replenished. The mass efficiency of space agriculture is poor. On Earth, agricultural systems benefit from deep soil, natural water cycles, sunlight, and a stable environment maintained by the planet's massive thermal inertia. In space, everything must be artificial. Studies suggest that even with highly efficient hydroponic or aeroponic systems, the equipment mass per person fed is hundreds of kilograms. For a crew of 10, a self-sustaining agricultural system might mass several tons, not counting the mass of stored nutrients, spare parts, and backup systems. Moreover, agricultural systems are living ecosystems that can fail unpredictably. Diseases can wipe out crops, equipment failures can cause cascading ecological collapse, and small imbalances in nutrients or environmental conditions can lead to crop failures. On Earth, failed crops can be replaced from other regions. On a spacecraft decades from Earth, a crop failure could be a death sentence. Waste management is another critical challenge. Humans produce approximately 150 grams of feces and 1.5 liters of urine per day, plus various other waste products from food packaging, equipment, and normal operations. All of this must be processed, recycled, or stored. The ISS currently vents some waste products into space and returns others to Earth for disposal. Neither option is available for an interstellar mission. Solid waste must be processed to recover water, nutrients, and any useful materials. This requires biological or chemical breakdown processes that themselves require energy, produce byproducts, and need maintenance. Over decades, these systems must process tons of waste without failure, degradation, or buildup of toxic byproducts. Temperature control is critical and challenging. Humans can survive only in a narrow temperature range. The spacecraft's interior must be maintained between approximately 18 and 24 degrees Celsius. In space, temperature control is difficult because the only way to shed heat is through thermal radiation. The spacecraft will be heated by sunlight when near a star, by equipment operations continuously, and by human metabolism. All this heat must be radiated away by radiators, which are massive structures that add significant weight and complexity. Air pressure must be maintained within a narrow range. The cabin must be pressurized to allow humans to breathe normally, but the pressure must be carefully controlled to prevent both hypoxia at too low pressure and oxygen toxicity at too high partial pressures of oxygen. Over decades, atmospheric leakage through hull micropenetrations, seal degradation, and airlocks usage will gradually reduce pressure unless continuously compensated. These life support systems are extraordinarily complex, with thousands of components that must all function correctly. Filters, pumps, sensors, control systems, valves, tanks, tubing, electrical connections, and countless other parts must operate for decades without access to replacement components beyond what was carried from Earth. The probability that all systems will function perfectly for 40 years is essentially zero. Each component has a mean time between failures. Even if each component is highly reliable, failing only once per 1,000 hours on average, in a system with thousands of components operating continuously for 40 years, you would expect thousands of failures. Some can be repaired, but repairs require spare parts, tools, and expertise. Carry too many spares and your spacecraft becomes too massive. Carry too few and a single irreparable failure ends the mission. The complexity creates fragility. Systems depend on other systems and cascading webs of dependencies. A failure in the power system affects life support. A failure in temperature control affects equipment reliability. A water recycling failure increases oxygen system load. These cascading failures can create situations where multiple critical systems fail simultaneously, overwhelming the crew's ability to respond. There's also the training problem. The crew must be experts in biology, chemistry, engineering, medicine, agriculture, and numerous other fields to maintain and repair all these systems. They must diagnose problems, improvise solutions with limited resources, and keep everything running for decades. The cognitive load is enormous, and as we discussed earlier, radiation-induced cognitive decline makes this task increasingly difficult over time. The fundamental issue is that life support systems must approach perfect efficiency and reliability over timescales that far exceed anything we've achieved in human spaceflight. The longest continuous human presence in space is the International Space Station, which has operated for about 25 years but has been continuously resupplied from Earth with replacement parts, new equipment, and fresh consumables. Remove that resupply capability, and the station would fail within months. An interstellar spacecraft cannot be resupplied. It must carry everything it needs for the entire mission. This creates impossible mass requirements when you factor in adequate redundancy and spare parts for decades of operations. And even with perfect planning, unexpected failures will occur. Equipment will break in ways engineers didn't anticipate, operating conditions will differ from models, and human error will introduce problems that cannot be predicted or prepared for. The life support challenge is not about building better recycling systems or more efficient agricultural technologies. It's about maintaining perfect operations of incredibly complex systems over timescales that exceed human institutional memory, in an environment where a single critical failure means everyone dies. This requirement for sustained perfection in a complex system is fundamentally at odds with engineering reality, where all systems eventually fail and redundancy can only delay but not eliminate that inevitable failure. While the technical challenges of life support are daunting, they pale in comparison to the psychological impossibilities of long-duration space missions. Human psychology evolved in the context of Earth's environment, with social structures, natural scenery, weather, seasons, and vast spaces to move through. The confined, monotonous environment of a spacecraft would create psychological stresses that are not just difficult but ultimately incompatible with mental health over the timescales required for interstellar travel. Consider the environment aboard an interstellar spacecraft. The habitable volume would be strictly limited by mass constraints. Every cubic meter of pressurized space requires hull material, life support capacity, and energy to heat and maintain. The crew would likely be confined to spaces smaller than a suburban house, perhaps only a few hundred cubic meters per person. These spaces would have no windows to the outside, or only small portholes, because large windows create structural weakness and radiation entry points. The environment would be utterly monotonous. The same walls, the same corridors, the same faces, day after day, year after year, decade after decade. There would be no weather, no seasons, no variation in environment except what is artificially created. The soundtrack would be the constant hum of ventilation and equipment. The smell would be recycled air, machinery, and other humans. There's no away on a spacecraft, no fresh air, no escape from the odors of close confinement. Studies of long-duration isolation on Earth provide disturbing insights into what this would do to the human psyche. Research stations in Antarctica, submarines, and isolation experiments consistently show that humans under extended confinement develop a range of psychological problems. Depression, anxiety, interpersonal conflicts, and decreased cognitive performance are nearly universal. And these Earth-based studies involve missions lasting months to perhaps a few years, with the knowledge that return to normal life is possible and the ability to communicate with the outside world. An interstellar mission would involve isolation lasting decades, with no possibility of return within the crew's lifetime, and communication delays measured in years. The psychological impact would be devastating. Crew members would know that everyone they left behind is aging or dying while they float in a tin can through the void. They would never again see a sunset, feel wind or rain, walk on grass, swim in an ocean, or experience any of the environmental stimuli that human psychology requires. Social dynamics would become toxic over time. Research on isolated groups shows that conflicts inevitably develop, even among carefully selected and trained individuals. People develop grievances, form factions, engage in status competitions, and generally make life miserable for each other. In normal society, people experiencing conflict can separate, find new social groups, or physically remove themselves from stressful situations. On a spacecraft, there is no escape. You're locked in with the same people forever, and any interpersonal conflicts become inescapable sources of chronic stress. The authority structure would also create problems. Someone must be in command, making final decisions about resource allocation, conflict resolution, and mission priorities. But what gives them this authority decades into the mission? The government that appointed them no longer exists in any form they'd recognize. The legal framework undergirding their authority is meaningless light years from Earth. Maintaining discipline and cooperation in such circumstances would be nearly impossible. There's also the problem of purpose and meaning. Human psychology requires goals, progress toward objectives, and a sense that one's efforts matter. The crew of an interstellar mission would spend decades performing maintenance tasks, monitoring systems, and essentially waiting. Any scientific observations made during the journey could be transmitted to Earth at light speed, arriving years or decades before the spacecraft itself. The crew would know that their personal presence adds little value beyond keeping the spacecraft operational, and even that task would be better performed by robots if we had sufficiently advanced automation. This purposelessness would be psychologically crushing. Studies of unemployment and retirement show that humans need meaningful work to maintain mental health. Busy work and make-work projects don't fulfill this need. People recognize when their efforts are fundamentally pointless. The crew would be aware that they're essentially living cargo, kept alive so that human bodies can be delivered to another star system for no clear reason other than that someone decades ago decided to send them. The sensory deprivation would also take a toll. Humans evolved in environments rich with sensory input, varied visual scenes, complex sounds, diverse textures and tactile experiences, and the full range of natural phenomena. A spacecraft provides minimal sensory stimulation. Virtual reality might provide temporary relief, but VR systems would need to function for decades, require substantial power and computing resources, and would only highlight the contrast between the rich simulated environment and the impoverished reality. Over time, crew members would likely develop a range of psychological disorders. Depression would be nearly universal given the circumstances. Anxiety disorders would develop from the knowledge that any system failure could be fatal and that survival depends on equipment continuing to function far beyond its designed lifetime. Paranoia might develop, with crew members becoming hypervigilant about potential problems and suspicious of each other's competence. Some crew members might develop dissociation disorders, psychologically detaching from their circumstances as a coping mechanism. Others might experience declining motivation, finding it increasingly difficult to perform even basic tasks. Suicidal ideation would likely be common, though actual suicide would be complicated by the impact it would have on the remaining crew and the ethical questions about depriving them of a trained member. Interpersonal relationships would be incredibly fraught. Romantic relationships that begin hopefully would likely deteriorate under the stress of permanent confinement. New relationships might form, but with a limited pool of potential partners and no possibility of distance or separation, these would be psychologically unhealthy. Children born aboard would face their own unique psychological challenges, growing up in an environment fundamentally unsuited for human development, never experiencing Earth or anything resembling a natural environment. The cognitive effects of chronic stress would compound the radiation-induced cognitive decline discussed earlier. Chronic stress causes measurable changes in brain structure, particularly in the hippocampus, affecting memory and learning. Sleep disorders would be common given the disrupted circadian rhythms from absence of natural day-night cycles. Poor sleep would further impair cognitive function, creating a downward spiral of declining mental capacity. There's no solution to these psychological problems. You cannot engineer away the human need for varied environments, social connections beyond a tiny group, purposeful activity, and hope for the future. You cannot train people to be psychologically resilient enough to endure decades of such conditions. You cannot select individuals immune to these problems because no such individuals exist. The psychological requirements for such a mission are fundamentally incompatible with human nature as shaped by millions of years of evolution on Earth. Some have proposed a different approach to avoid the psychological challenges of such long missions, generation ships, where multiple generations of humans would be born, live, and die aboard the spacecraft, with only distant descendants reaching the destination. This concept appears in countless science fiction stories, but examination of the practical realities reveals that generation ships are perhaps the most problematic proposal of all, raising both technical and ethical issues that render them essentially impossible. The first challenge is the population genetics of a small isolated group. For a population to remain genetically healthy over many generations, it needs sufficient genetic diversity. This means a generation ship would need to carry not 10 or 20 people but hundreds or thousands. Each person requires life support, living space, food, water, and shares of all spacecraft resources. The mass requirements scale linearly with population size. A spacecraft designed for 1,000 people would need to be vastly larger and more massive than one for 10 people, with corresponding increases in energy requirements for propulsion and all the other problems we've discussed. The social dynamics of generation ships are even more problematic than their physical requirements. You would be creating a society that exists solely to maintain a spacecraft and reach a destination that the current generation will never see. How do you motivate people to maintain systems and follow protocols when they know they'll never benefit from the mission's success? Why would anyone born aboard the spacecraft care about reaching Proxima Centauri when they have no connection to Earth and no experience of life anywhere but the spacecraft? Historical examples of isolated communities provide cautionary tales. Isolated island populations and experimental communes consistently develop social problems. Power structures become tyrannical or break down entirely. Social norms drift from those of the parent culture in unpredictable ways. Conflicts over resources, mates, and status create factions and sometimes violence. Innovation stagnates because the small population lacks diversity of thought and approach. A generation ship would face all these problems amplified by the closed environment and the fact that leaving is impossible. Social conflicts that might be resolved through physical separation on Earth have no such escape valve on a spacecraft. Factions that develop incompatible beliefs cannot split and go their separate ways. Revolutionary movements that reject the mission's purpose cannot be suppressed without creating a prison environment. There's also the ethical question: what right does the initial generation have to condemn their children, grandchildren, and distant descendants to lives imprisoned on a spacecraft? These future people never consented to the mission. They had no choice about their circumstances. They will live their entire lives in an artificial environment, never seeing planets or stars except as distant lights, never experiencing the diversity and richness of life on a world, all because their ancestors decided to undertake a mission whose purpose and value will likely seem increasingly questionable as generations pass. If descendants decide they don't want to continue the mission, what happens? Can they turn around? Probably not. The energy required to reverse course and return to Earth would be prohibitive. Can they stop somewhere else, perhaps an intermediate system? There's nowhere to stop in interstellar space. They're committed to their trajectory by physics and the irrecoverable expenditure of fuel that got them moving in the first place. Education becomes a critical problem. Each generation must be trained to maintain incredibly complex systems. This requires preserved knowledge, effective teaching, and motivated students. But over generations, knowledge can be lost. If a critical expert dies before fully training replacements, expertise disappears. If social upheaval disrupts education, a generation might grow up without the skills needed to maintain the ship. If the society aboard the ship develops anti-intellectual movements that reject scientific knowledge, the technical capabilities could degrade over generations. Historical literacy provides examples. The knowledge to build Roman concrete was lost for centuries. The location of Troy was forgotten. Libraries burned, and the knowledge they contained vanished. On Earth, lost knowledge can sometimes be rediscovered or preserved elsewhere. On a generation ship, there is no elsewhere. Lost knowledge is simply gone, and if that knowledge concerns critical ship systems, the result is catastrophic failure. The population must also remain stable. Too many births and you exceed life support capacity. Too few and the population shrinks and ages, potentially falling below the minimum viable population. This requires either enforced birth limits, which restrict fundamental human freedoms, or allowing the population to fluctuate with the risk of catastrophic overpopulation or extinction. There's no good solution to this demographic problem. Without the moderating influence of a larger society and with the closed environment amplifying any cultural innovations, strange and potentially dysfunctional belief systems could emerge. We've seen this in small isolated communities on Earth. A generation ship would be even more isolated, and over decades or centuries, the culture could evolve in directions that make mission completion impossible. There's also the question of who has authority across generations. The original mission planners are centuries dead. Their instructions and plans were created for conditions they could only guess at. Why should descendants follow plans made by people who've been dead for generations for a purpose that may no longer seem relevant? Yet if each generation renegotiates the mission goals, the ship might never reach its destination or might arrive with completely different objectives than the original mission intended. The generation ship concept ultimately fails because it attempts to create a stable, multi-generational society in the most unstable and constrained environment imaginable. Human societies on Earth, with vast spaces, abundant resources, and the ability to expand and migrate, still frequently collapse or transform beyond recognition. A society confined to a spacecraft, with strictly limited resources and no possibility of expansion or escape, would face far greater challenges with far fewer tools to address them. The generation ship represents not a solution to interstellar travel but an unconscionable gamble with the lives of people who never agreed to be part of the experiment. It's a proposal that ignores human psychology, social dynamics, and ethics in pursuit of a goal that could be better served by robotic probes or by accepting that interstellar travel is not something humans are meant to accomplish. Speaking of things we cannot accomplish, there's a physical principle even more fundamental than the challenges we've discussed so far: the problem of deceleration. This might seem like a technical detail, but it's actually one of the most devastating barriers to interstellar travel because it effectively doubles all the impossible energy requirements we've already discussed. Every physics student learns Newton's first law: an object in motion stays in motion unless acted upon by an external force. In space, without air resistance or friction, a spacecraft accelerated to high velocity will continue at that velocity indefinitely. This sounds beneficial until you realize it becomes a catastrophic problem when you want to stop. Imagine you've somehow solved all the previous problems and accelerated a spacecraft to 10% of light speed for a journey to Proxima Centauri. The spacecraft is hurtling through space at 30,000 kilometers per second. As you approach your destination, you need to slow down. You can't just slam on the brakes. There are no brakes in space. The only way to decelerate is to expend thrust in the opposite direction to your motion, which requires fuel. Here's the devastating reality. The amount of energy needed to decelerate from 10% of light speed is exactly equal to the energy needed to accelerate to that speed in the first place. You need just as much fuel for deceleration as you needed for acceleration. This doesn't just double your fuel requirements. It more than doubles them because of the rocket equation we discussed earlier. Remember, fuel has mass, and you need fuel to accelerate fuel. If you need X amount of fuel to accelerate your payload to your target velocity, you need additional fuel to accelerate that fuel, and more fuel to accelerate the fuel that accelerates the fuel, in an exponential spiral. But it gets worse. You need to carry all your deceleration fuel with you during the acceleration phase, which means you need even more acceleration fuel to carry the deceleration fuel. The mathematics become devastating. Let's work through a simplified example. Suppose you have a 1-ton payload and you've calculated that you need 10 tons of fuel to accelerate it to your target velocity. Now you need to add deceleration capability. Your deceleration fuel needs to slow down not just the 1-ton payload but also itself. If you need 10 tons for deceleration, your payload for the acceleration phase isn't 1 ton, it's 11 tons, 1 ton of actual payload plus 10 tons of deceleration fuel. To accelerate 11 tons to your target velocity, you now need 110 tons of acceleration fuel instead of 10. But wait, you also need to carry that 110 tons of fuel during acceleration, which increases your total mass and requires even more fuel. The actual calculations involve solving exponential equations and typically result in mass ratios that are absurd, often thousands or tens of thousands to 1. For chemical rockets with relatively low exhaust velocities, the mass ratios quickly become physically impossible. Even for more efficient propulsion systems, the requirements spiral into implausibility. To accelerate, and then decelerate a modest spacecraft to just 10% of light speed would require mass ratios that mean your initial spacecraft would need to be larger than small moons, consisting almost entirely of fuel with the actual payload being an infinitesimal fraction of the total. Some have proposed alternative deceleration methods to avoid carrying fuel for slowing down. One idea is aerobraking, using a planet's atmosphere to slow the spacecraft. This works for missions within our solar system, where spacecraft can enter planetary atmospheres at relatively modest velocities and use atmospheric friction to decelerate. But for interstellar missions, it's completely impractical. At 10% of light speed, a spacecraft hitting an atmosphere would experience forces and heating that would instantly vaporize it. The kinetic energy to be dissipated is enormous. Remember our earlier calculation about grain of sand impacts, and there's no material that could survive the plasma inferno that would be created. Even if there were, the deceleration forces would be thousands of Gs, instantly killing any crew and destroying any equipment. Another proposal is magnetic braking, using the spacecraft's magnetic field to interact with the interstellar medium and gradually slow down. This theoretically works but faces severe practical problems. The interstellar medium is so diffuse that the braking effect would be minimal unless you had absolutely enormous magnetic sails, structures kilometers or tens of kilometers across. Creating and maintaining such fields requires tremendous power. And the process would take years or decades, during which the spacecraft would be traveling far past its destination star system, eventually coming to rest in interstellar space far from anywhere useful. Gravitational assists, or slingshot maneuvers, allow spacecraft to change velocity by passing close to massive objects and exploiting their gravitational fields. These are routinely used for missions within our solar system. But they require a gravitating body to be conveniently positioned along your route, which you cannot guarantee for interstellar missions. Moreover, gravitational assists typically work for relatively modest velocity changes, not for shedding 10% of light speed. Light sails face a particularly acute deceleration problem. The concept is to use large, ultra-thin reflective sails pushed by laser light from the home star system. This elegantly avoids the rocket equation for acceleration because you're not carrying fuel. But how do you slow down? The laser that pushed you is now light years behind you. You can't turn around and use it to decelerate because turning a light sail around while traveling at high velocity requires propulsion, bringing us back to the fuel problem. Some proposals suggest using the destination star's light pressure to slow down. But stellar light pressure is far too weak to decelerate a spacecraft in any reasonable distance. You would sail past the destination star and continue into deep space before slowing significantly. Others propose a second laser system at the destination to slow the spacecraft, but this requires having already established infrastructure at the destination, which is impossible on a maiden voyage to a new star system. The most elaborate proposal involves detaching the sail partway through the journey and using the detached portion as a reflector to bounce the home system's laser light back at the spacecraft, using that reflected light pressure to decelerate. This theoretical concept, called beam-driven deceleration, faces enormous practical challenges. You need fantastically precise positioning and control over light-year distances. The reflected light would be incredibly diffuse and weak, and any small error in alignment would cause the spacecraft to miss the reflected beam entirely. There's also the magnetic sail concept, where you use a superconducting loop to create a magnetic field that interacts with the interstellar medium's charged particles to provide both acceleration and deceleration. But as mentioned, the interstellar medium is so diffuse that the forces generated are minimal. Accelerating to significant velocities would take decades or centuries of continuous operation, and the magnetic fields required would be enormous, requiring substantial infrastructure that adds mass and complexity. Every proposed solution to the deceleration problem either requires carrying fuel, which brings us back to the mass ratio nightmare, or relies on infrastructure or environmental conditions that don't exist or can't be guaranteed. The simple reality is that Newton's laws of motion are unforgiving. You need to apply force opposite to your motion to slow down, and applying force in space requires some form of reaction mass or external momentum transfer. There's no magical solution. This creates a paradox. The faster you go, the harder the deceleration problem becomes, but going slower makes journey times impractical. You're trapped between impossibly long missions at low velocities and impossible deceleration requirements at high velocities. There's no sweet spot where both problems are manageable. Some might suggest simply not decelerating, conducting a high-speed flyby of the destination system, making observations during the brief time you're close enough, then continuing into deep space. For robotic probes, this might make sense for some scientific questions. But for crewed missions, it's pointless. You spend decades accelerating, decades in transit, experience all the radiation exposure and psychological stress, and then flash past your destination in hours or days, unable to stop, unable to explore, continuing into the void until your life support fails. The deceleration problem fundamentally undermines the practicality of interstellar travel. It's not enough to solve the propulsion problem. You need to solve it twice, once for acceleration and again for deceleration, with the added complexity that solutions for one phase often create new problems for the other. This doubling of the energy requirement, already impossible for acceleration alone, places interstellar missions definitively beyond the realm of physical possibility with any conceivable technology. Even if we manage to somehow hand-wave away all these physical barriers, the energy, the propulsion, the deceleration, we would face another absolute limitation, the speed of light limit on communication. This might seem less immediately threatening than radiation or impact hazards, but it creates an informational isolation that makes interstellar missions fundamentally pointless from a practical standpoint. Einstein's relativity tells us that information cannot travel faster than light. This isn't a technological limitation but a fundamental feature of space-time. Light speed isn't just the fastest we can transmit signals, it's the speed at which causality itself propagates. Events cannot influence each other if they're separated by more space than light can cross in the available time. This creates an inescapable isolation for any interstellar mission. Consider communications with a mission to Proxima Centauri, our nearest stellar neighbor at 4.24 light-years distance. Any message sent from the spacecraft to Earth takes 4.24 years to arrive, traveling at light speed. A response from Earth takes another 4.24 years to return. The round-trip communication time is 8.48 years. Ask a question and receive an answer nearly 9 years later. This communication lag makes any form of real-time collaboration, assistance, or decision-making impossible. If the spacecraft encounters a problem requiring expert help from Earth, the crew must solve it themselves because by the time they send a distress signal and receive a response, they'll be dead or the situation will have resolved itself one way or another. Mission control cannot guide the mission in any meaningful sense. They can send information and suggestions, but these arrive years after being sent, addressing situations that may no longer exist. The psychological impact of this communication void is profound. Phone calls with family are impossible. Video messages sent home today receive responses years later. By the time you receive a message from your children, they're years older than when they recorded it. Conversations become asynchronous exchanges stretched across years, making maintaining any relationship impossible. You're sending messages to people who will be different people by the time they receive them, and they're sending messages to a version of you that no longer exists by the time they arrive. News from Earth arrives years out of date. Major historical events, scientific breakthroughs, cultural shifts, all are ancient history by the time you learn about them. You exist in an information bubble, isolated from the forward march of human civilization. The world you left continues without you, and you receive only distant echoes of its evolution, always years behind, never current, never connected. For mission operations, this creates severe constraints. Every decision must be made autonomously. The crew cannot consult with experts on Earth about unexpected situations. They cannot receive updates to software when bugs are discovered. They cannot benefit from technological advances made during their journey. They're frozen in time, working with knowledge and technology from the departure date, while Earth continues advancing. Scientific missions face particular challenges. If the spacecraft makes a discovery that raises new questions, scientists on Earth cannot redirect the mission to investigate further. By the time the question reaches Earth and instructions return, the opportunity will be gone. The spacecraft must be programmed with sufficient autonomy and flexibility to make its own scientific decisions, but this is extraordinarily difficult for complex exploratory missions where you don't know what you'll find. The communication delay also affects coordination between multiple missions. If you send several spacecraft to different destinations, they cannot coordinate with each other except on timescales of years or decades. Building any kind of distributed infrastructure or network across interstellar distances is impossible when communication takes years and all coordination must be planned decades in advance with no ability to adjust to changing circumstances. There are strategic implications as well, though these are less relevant for scientific missions. Any space-based economy or civilization spread across multiple star systems would be fundamentally different from anything we've experienced on Earth. Trade would be impossible. By the time goods arrived, years or decades would have passed and market conditions would have completely changed. Cultural exchange would be minimal. No government could govern territories years apart in communication. Each star system would be essentially independent, with communication being more like historical correspondence between civilizations than real-time interaction. Some science fiction proposes faster-than-light communication through quantum entanglement, or other exotic physics. But quantum entanglement cannot transmit information faster than light. This is a common misconception. While entangled particles exhibit correlated properties, you cannot use this correlation to send messages. Any attempt to do so reduces to classical communication limited by light speed. Other proposed FTL communication methods, like tachyons or wormholes, are purely speculative and likely impossible according to our understanding of physics. The communication void also affects how we could use data from interstellar missions. Scientific observations transmitted back to Earth arrive years after being made. Researchers working with this data must wait years between sending questions and receiving clarifications. Any interactive exploration or experimentation is impossible. You plan your observations years in advance, execute them, wait years for results, then wait more years if you want to follow up. The pace of research would be glacial. For human missions, the communication delay creates existential questions. Why send humans if they cannot be guided, supported, or integrated with Earth-based efforts? What value do human observers add if their observations take years to reach Earth, and they cannot be redirected based on what they find? Robotic missions face the same communication delays, but robots don't suffer psychologically from isolation, don't need the life support that humans require, and can be designed to operate autonomously more easily than humans can be trained to do so. The communication problem is unsolvable. Light speed is not an engineering challenge, but a fundamental limit. No technology, no matter how advanced, can transmit information faster than light without violating causality itself. If FTL communication were possible, it would allow sending messages into the past, creating temporal paradoxes that seem to make such communication logically impossible. We're stuck with light speed, and light speed is far too slow for the distances involved in interstellar travel. This means that any interstellar mission is fundamentally isolated, cut off from humanity in an informational sense even more profoundly than in a physical sense. The crew would be making decisions years before Earth could even know those decisions needed to be made, living lives that Earth learns about only through messages from the past, existing in a bubble of space and time that cannot be penetrated by any communication faster than the light that struggles across the void at its absolute limiting speed. While the communication delay creates intellectual and emotional isolation, the physical isolation is maintained by an even more insidious problem: the gradual, inevitable degradation of equipment through entropy. All machines break down over time, and in the hostile environment of space, far from any repair facilities, the breakdown of critical systems would lead to certain mission failure and likely death for any crew. The second law of thermodynamics tells us that entropy always increases in closed systems. More practically, this means everything breaks down. Materials degrade, moving parts wear out, electronic components fail, and complex systems drift away from their designed operating parameters. On Earth, we manage this through maintenance, repairs, and replacement of worn components. We have vast industrial infrastructures to manufacture spare parts, extensive supply chains, and easy access to materials and expertise. In interstellar space, you have only what you brought with you. Consider the lifespan of typical spacecraft components. Electronic components, especially those exposed to radiation, have limited operational lifetimes. Cosmic rays can cause single-event upsets, flipping bits in computer memory and causing malfunctions. Over time, radiation damage accumulates, degrading semiconductors until they fail. Redundant systems help, but eventually, redundancy is exhausted. Mechanical systems face their own degradation. Bearings wear, seals deteriorate, lubricants break down, and metals fatigue from repeated stress cycles. The ISS, after 25 years in operation, has been continually maintained and repaired, with worn components replaced during regular resupply missions. Without this constant maintenance, it would have failed long ago. An interstellar spacecraft has no resupply missions, no hardware store to visit, no possibility of ordering replacement parts. Radiation affects not just electronics but structural materials. High-energy particles knock atoms out of lattice positions in metals, creating defects that accumulate over time. This radiation damage makes materials brittle, weakening structural components. After decades of exposure to cosmic radiation, critical structural elements might fail catastrophically without warning. Thermal cycling, the constant expansion and contraction of materials as temperatures fluctuate, creates fatigue stresses. Every time the spacecraft passes through a region where solar heating increases or uses onboard systems that generate heat, materials expand. When it cools, they contract. Over thousands or millions of these cycles during a multi-decade mission, fatigue cracks develop. These cracks propagate until structures fail. Micrometeorite impacts, even those too small to cause immediate catastrophic damage, create tiny cracks and divots in the spacecraft's exterior. Each impact is a starting point for stress concentration and crack propagation. Over decades, the hull becomes increasingly weakened, like a windshield with a small chip that eventually spreads into a massive crack. Chemical degradation affects everything from hull materials to life support consumables. Polymers break down under UV exposure and oxidation. Metals corrode in the presence of moisture and atmospheric contaminants. The closed environment of a spacecraft means that corrosive substances, once introduced, cannot be easily removed. They circulate through the atmosphere and water systems, slowly attacking everything they contact. Energy storage systems degrade over time. Batteries lose capacity through repeated charge-discharge cycles. Solar panels lose efficiency as radiation damage accumulates in their semiconductor layers and as micrometeorite impacts gradually erode their surfaces. Nuclear power systems deplete their fuel and accumulate reaction products that poison the reaction. After decades, power output inevitably declines. Computer systems face unique challenges. Data corruption from radiation, thermal stress, and simple age will accumulate. Error-correcting codes can fix some problems, but eventually, errors overwhelm correction capabilities. Storage media degrade, magnetic domains relax, flash memory loses charge, optical media deteriorate. The software and data needed to operate the spacecraft could become corrupted beyond recovery. Complex systems develop emergent failures that weren't anticipated during design. Interactions between components create failure modes that no amount of testing on Earth could reveal because they only manifest after years of operation in space conditions. When these unexpected failures occur, the crew must diagnose and repair them with limited resources and no support from Earth. Spare parts present an impossible dilemma. Carrying spares for everything would add enormous mass. Each additional kilogram of spare parts is a kilogram that requires fuel to accelerate and decelerate, exacerbating all our previous problems. But not carrying spares means accepting that certain failures will be irreparable. The spacecraft becomes a machine with thousands of components, any of which might fail, and only a subset of which can be replaced. How do you decide which spares to carry? You might bring redundant life support systems, multiple power generators, backup computers. But what about specialized sensors, unique structural components, custom manufactured parts that cannot be fabricated aboard? What about simple things like gaskets, fasteners, bearings? A spacecraft might contain hundreds of thousands of individual parts. Carrying even one spare for each would be prohibitively massive. The ability to manufacture replacement parts aboard might help, but 3D printers and machine shops have their own reliability issues and can only make certain types of components. You cannot 3D print advanced electronics, precision optical systems, or many other critical parts. The materials you can work with are limited to what you brought. Once the supply of raw materials is exhausted, no more parts can be made. Tools themselves wear out and break. Machine tools need maintenance and replacement parts. Even hand tools eventually fail. A broken wrench seems trivial until you need that specific size and don't have it. The entire workshop infrastructure needed to maintain a spacecraft would itself need maintenance, creating a recursive problem. Knowledge degradation is another form of entropy. Crew members forget details of complex systems, especially those not used regularly. Training materials can be stored digitally, but require functioning computers to access. Physical manuals degrade over time. The institutional knowledge about obscure systems, undocumented quirks, and informal workarounds exists only in crew members' heads and is lost if those individuals die or become incapacitated before passing it on. As systems fail and workarounds are implemented, the spacecraft's configuration drifts away from its design state. Documentation becomes outdated. Future repairs become more difficult because the system is no longer in a known configuration. Diagnostic procedures fail because they assume the original setup. This drift makes the spacecraft progressively harder to maintain. There's also the problem of cascading failures. When one system fails, it increases stress on backup systems, making them more likely to fail. Power system failures affect life support. Life support problems affect crew health, reducing their ability to perform repairs. Reduced repair capability leads to more failures. The spacecraft enters a death spiral where each failure makes subsequent failures more likely and more severe. Radiation affects not just electronics but structural materials. High-energy particles knock atoms out of lattice positions in metals, creating defects that accumulate over time. This radiation damage makes materials brittle, weakening structural components. After decades of exposure to cosmic radiation, critical structural elements might fail catastrophically without warning. Thermal cycling, the constant expansion and contraction of materials as temperatures fluctuate, creates fatigue stresses. Every time the spacecraft passes through a region where solar heating increases or uses onboard systems that generate heat, materials expand. When it cools, they contract. Over thousands or millions of these cycles during a multi-decade mission, fatigue cracks develop. These cracks propagate until structures fail. Micrometeorite impacts, even those too small to cause immediate catastrophic damage, create tiny cracks and divots in the spacecraft's exterior. Each impact is a starting point for stress concentration and crack propagation. Over decades, the hull becomes increasingly weakened, like a windshield with a small chip that eventually spreads into a massive crack. Chemical degradation affects everything from hull materials to life support consumables. Polymers break down under UV exposure and oxidation. Metals corrode in the presence of moisture and atmospheric contaminants. The closed environment of a spacecraft means that corrosive substances, once introduced, cannot be easily removed. They circulate through the atmosphere and water systems, slowly attacking everything they contact. Energy storage systems degrade over time. Batteries lose capacity through repeated charge-discharge cycles. Solar panels lose efficiency as radiation damage accumulates in their semiconductor layers and as micrometeorite impacts gradually erode their surfaces. Nuclear power systems deplete their fuel and accumulate reaction products that poison the reaction. After decades, power output inevitably declines. Computer systems face unique challenges. Data corruption from radiation, thermal stress, and simple age will accumulate. Error-correcting codes can fix some problems, but eventually, errors overwhelm correction capabilities. Storage media degrade, magnetic domains relax, flash memory loses charge, optical media deteriorate. The software and data needed to operate the spacecraft could become corrupted beyond recovery. Complex systems develop emergent failures that weren't anticipated during design. Interactions between components create failure modes that no amount of testing on Earth could reveal because they only manifest after years of operation in space conditions. When these unexpected failures occur, the crew must diagnose and repair them with limited resources and no support from Earth. Spare parts present an impossible dilemma. Carrying spares for everything would add enormous mass. Each additional kilogram of spare parts is a kilogram that requires fuel to accelerate and decelerate, exacerbating all our previous problems. But not carrying spares means accepting that certain failures will be irreparable. The spacecraft becomes a machine with thousands of components, any of which might fail, and only a subset of which can be replaced. How do you decide which spares to carry? You might bring redundant life support systems, multiple power generators, backup computers. But what about specialized sensors, unique structural components, custom manufactured parts that cannot be fabricated aboard? What about simple things like gaskets, fasteners, bearings? A spacecraft might contain hundreds of thousands of individual parts. Carrying even one spare for each would be prohibitively massive. The ability to manufacture replacement parts aboard might help, but 3D printers and machine shops have their own reliability issues and can only make certain types of components. You cannot 3D print advanced electronics, precision optical systems, or many other critical parts. The materials you can work with are limited to what you brought. Once the supply of raw materials is exhausted, no more parts can be made. Tools themselves wear out and break. Machine tools need maintenance and replacement parts. Even hand tools eventually fail. A broken wrench seems trivial until you need that specific size and don't have it. The entire workshop infrastructure needed to maintain a spacecraft would itself need maintenance, creating a recursive problem. Knowledge degradation is another form of entropy. Crew members forget details of complex systems, especially those not used regularly. Training materials can be stored digitally, but require functioning computers to access. Physical manuals degrade over time. The institutional knowledge about obscure systems, undocumented quirks, and informal workarounds exists only in crew members' heads and is lost if those individuals die or become incapacitated before passing it on. As systems fail and workarounds are implemented, the spacecraft's configuration drifts away from its design state. Documentation becomes outdated. Future repairs become more difficult because the system is no longer in a known configuration. Diagnostic procedures fail because they assume the original setup. This drift makes the spacecraft progressively harder to maintain. There's also the problem of cascading failures. When one system fails, it increases stress on backup systems, making them more likely to fail. Power system failures affect life support. Life support problems affect crew health, reducing their ability to perform repairs. Reduced repair capability leads to more failures. The spacecraft enters a death spiral where each failure makes subsequent failures more likely and more severe. The statistics are brutal. If you have a complex spacecraft with thousands of critical components, and each component has a mean time between failures of, say, 10,000 hours, you will experience hundreds of failures during a 40-year mission. Some can be repaired, some have redundant backups, but eventually, a critical component will fail without a viable repair option. Mission over. Earth-based systems avoid this fate through continuous maintenance by teams of specialists, replacement of worn parts, upgrades to newer technology, and complete overhauls when necessary. We have industries dedicated to producing replacement parts, experts who specialize in specific systems, and the ability to call for help when problems exceed local expertise. Remove all of this support, and even our most robust systems would fail within years. An interstellar spacecraft cannot be maintained at the level needed for reliable decades-long operation. It's a machine sent into the most hostile environment imaginable, subjected to radiation, thermal stress, impacts, and vibration, with no repair facilities, limited spare parts, and a crew whose number and expertise are necessarily limited. The entropy problem is not just a challenge, but a guarantee that the mission will fail. The only question is when. We've discussed many challenges so far, but one of the most fundamental and overlooked is gravity, or rather, the lack of it. Human biology evolved under Earth's gravitational field for hundreds of millions of years. Every system in our bodies assumes the presence of approximately 1 g of acceleration toward the center of the planet. Remove that assumption, and our biology begins to fail in ways that are not just problematic but ultimately fatal. Astronauts on the ISS experience bone loss of approximately 1 to 2% per month in weight-bearing bones. This is an extraordinarily rapid loss, faster than severe osteoporosis on Earth. The body, sensing that the structural strength is not needed in zero gravity, begins dissolving bone tissue and excreting the calcium. Exercise regimes can slow this loss but not prevent it. After a year in space, astronauts have lost 10 to 20% of bone mass in critical areas. For an interstellar mission lasting decades, the bone loss would be catastrophic. Even with exercise, astronauts would arrive at their destination with skeletal systems too weak to support their body weight under any significant gravity. Their bones would be fragile, prone to fractures from trivial impacts. They would be crippled, unable to explore any planet with substantial gravity, barely able to function even in fractional G environments. Muscle atrophy is equally severe. Without gravity to work against, muscles deteriorate rapidly. Despite hours of daily exercise on the ISS, astronauts lose significant muscle mass and strength. For decades-long missions, the muscle loss would be profound. Even with perfectly designed exercise protocols, and we don't have such protocols, crew members would arrive at their destinations significantly weakened. The cardiovascular system suffers multiple problems in zero gravity. Without gravity pulling blood toward the feet, blood redistributes toward the upper body and head. The heart, sensing this redistribution, shrinks because it doesn't need to pump as hard against gravity. Blood volume decreases. When astronauts return to Earth after long-duration missions, They experience orthostatic intolerance, difficulty standing without fainting, because their cardiovascular systems can no longer effectively pump blood against gravity. For an interstellar crew, decades in zero gravity would leave them with hearts too weak to function under any significant gravity. Returning to Earth or exploring a planet with Earth-like gravity would be impossible. Their cardiovascular systems, adapted to weightlessness, would fail under the stress of normal gravity. Vision problems are common among astronauts on long-duration missions. The fluid shifts caused by zero gravity increase intracranial pressure, which compresses the optic nerve and deforms the eyeball. This causes vision degradation that can be permanent. Some astronauts have returned from 6-month missions with permanent vision damage. What would decades in space do to their vision? The immune system weakens in space. Studies show that the immune response is suppressed in microgravity, making astronauts more susceptible to infections. The closed environment of a spacecraft ensures that any pathogens introduced are shared among the entire crew, and weakened immune systems would make infectious disease outbreaks more likely and more severe. Kidney stones are a serious concern. The bone loss in space releases calcium into the bloodstream, which is excreted through the kidneys. This increased calcium load leads to kidney stone formation at much higher rates than on Earth. Passing a kidney stone is excruciatingly painful under the best circumstances. In space, with limited medical facilities and no possibility of emergency medical evacuation, it could be life-threatening. Radiation exposure exacerbates all these problems. Radiation damages bone marrow, affecting blood cell production. It suppresses the immune system. It accelerates cardiovascular disease. The combination of microgravity and radiation creates synergistic effects worse than either alone. The obvious solution seems to be artificial gravity through rotation. If you spin a spacecraft, centrifugal force creates an outward acceleration that can simulate gravity. This concept is sound in principle but faces enormous engineering challenges in practice. To create Earth-like artificial gravity, you need either a very large radius of rotation or a high rotation rate. The relationship is given by the equation for centripetal acceleration. The acceleration equals the rotation rate squared times the radius. To create 1g with a comfortable rotation rate of a few rotations per minute requires a radius of hundreds of meters. The spacecraft would need to be enormous. Building a rotating structure hundreds of meters in radius that can withstand the stresses of continuous rotation for decades is extraordinarily challenging. Every connection point must be perfectly engineered because any imbalance creates vibrations that propagate through the structure. The mass of such a structure would be enormous, thousands or tens of thousands of tons, bringing us back to all the propulsion and energy problems we've discussed. A rotating spacecraft cannot easily change its orientation or thrust direction because of gyroscopic effects. The angular momentum stored in the rotation resists changes in orientation, requiring substantial force to redirect. This makes maneuvering difficult and complicates course corrections or emergency maneuvers. The rotation itself creates problems. The Coriolis effect means that moving objects follow curved paths rather than straight lines. This affects everything from walking to throwing objects to the behavior of fluids and plumbing systems. Humans can adapt to weak Coriolis forces, but the effect increases with rotation rate. Faster rotation means stronger Coriolis forces and more difficult adaptation. If the radius is too small, there's a significant gravity gradient from head to foot. Standing up, your feet experience more centrifugal force than your head, creating strange sensations and potentially nausea. The gradient also affects fluid distribution in the body in ways we don't fully understand because we've never tested humans in such environments for extended periods. Connecting the rotating sections to non-rotating sections, like docking ports, telescopes, or heat radiators that need to point in fixed directions, requires rotating seals and bearings. These mechanical interfaces are complex, prone to wear, and create potential failure points. Transferring power, fluids, and data across rotating interfaces is challenging and adds failure modes. If the rotation stops for any reason, mechanical failure, power loss, emergency maneuver, the crew is suddenly in zero gravity. All the physiological adaptations to the artificial gravity become maladaptive. If the rotation cannot be restarted, the crew faces all the health problems of zero gravity that the artificial gravity was meant to prevent. The size and mass requirements for effective artificial gravity essentially make it incompatible with interstellar missions. You must choose between a spacecraft light enough to accelerate to useful velocities and a spacecraft large enough to provide artificial gravity through rotation. You cannot have both because the mass and structural requirements are mutually exclusive with achievable propulsion capabilities. Some proposals suggest intermittent artificial gravity, rotating for only part of the day or using short radius centrifuges for exercise. But we don't know if partial gravity exposure is sufficient to prevent physiological decline. Studies on partial gravity are limited, and the long-term effects of living in fractional G environments for decades are completely unknown. We cannot assume it would be sufficient. The gravity problem is fundamental. Humans evolved for Earth gravity and require it for long-term health. Weightlessness causes progressive physiological damage that would cripple any crew during a decades-long journey. Artificial gravity is theoretically possible but practically incompatible with the mass and energy constraints of interstellar travel. We're trapped between our biological needs and physical limitations, with no viable middle ground. All of these challenges, radiation, impacts, life support, psychology, equipment degradation, gravity, are interconnected with another fundamental problem. Human biology itself is incompatible with space. We are not just Earth-dwellers. We are Earth-dependent organisms whose every biological system assumes the specific conditions of our home planet. Remove those conditions, and we begin to fail in ways that go beyond the specific challenges already discussed. Humans evolve over billions of years in Earth's environment. Our circadian rhythms are tuned to Earth's 24-hour day-night cycle. Disrupt these rhythms, and health consequences follow: sleep disorders, metabolic problems, immune suppression, and mood disorders. In space, without natural sunlight and Earth's rotation, maintaining proper circadian rhythms is difficult. Artificial lighting can help, but it's not equivalent to the complex spectral properties and timing of natural sunlight. Our respiratory system evolved to extract oxygen from air at Earth's atmospheric pressure and composition. While we can survive in a range of pressures and oxygen concentrations, deviations from Earth normal create stress. Pure oxygen at low pressure, as used in some spacecraft designs to reduce hull stress, causes long-term lung damage. Higher pressures require different gas mixtures and create other physiological challenges. Our cardiovascular system evolved to operate in Earth's temperature range. Humans maintain a narrow core body temperature, and deviations of even a few degrees are dangerous. In space, temperature regulation is challenging because the only way to shed heat is through radiation. The spacecraft must carefully balance heat generation from equipment and metabolism with heat loss through radiators, and any imbalance affects crew comfort and health. Our digestive system and gut microbiome evolved with Earth's bacteria, fungi, and other microorganisms. In the closed environment of a spacecraft, the microbial ecosystem shifts in unpredictable ways. Studies show that astronaut gut microbiomes change significantly during spaceflight, with potential implications for digestion, immune function, and overall health. Over decades, these microbial changes could have profound and unpredictable effects. Our sensory systems are calibrated for Earth. The inner ear, which provides balance information, becomes confused in zero gravity, often causing space adaptation syndrome, nausea and disorientation that can last days or weeks. Long-term sensory adaptation to space might create individuals who become disoriented and nauseous when exposed to normal gravity, essentially inverting the problem. The wound healing process assumes gravity. Fluid dynamics in wounds are different in zero gravity, potentially affecting healing rates and infection risks. Surgery in space would be extraordinarily difficult, with blood and other fluids forming floating globules rather than flowing predictably. Any serious injury or medical condition requiring surgery might be untreatable in space. Our psychology assumes the rich, varied sensory environment of Earth. As discussed earlier, the monotony of space creates psychological problems. But beyond monotony, our minds need certain environmental inputs: natural light, varied scenery, the presence of living things beyond our own species, for optimal functioning. These inputs are completely absent in space. Even our social evolution assumes communities larger and more diverse than could exist on a spacecraft. Human societies require networks of relationships, opportunities for new connections, and social structures larger than a few dozen or few hundred individuals. The social environment of a spacecraft would be impoverished in ways that undermine human psychological well-being. All of these biological incompatibilities with space are not engineering problems to be solved but mismatches between our evolved biology and the space environment. We could potentially engineer solutions to some of these problems, but each solution adds complexity, mass, power requirements, and failure modes to the mission. The aggregate of all these biological requirements makes supporting human life in space for decades or centuries an endeavor of such complexity that failure becomes inevitable. Moreover, even if we reached another planet, there's no reason to expect it would be biologically compatible with humans. Every potentially habitable exoplanet we've discovered has characteristics that differ from Earth: different atmospheric composition, different gravity, different day length, different stellar radiation spectrum, different seasonal patterns, and almost certainly completely different biochemistry if life exists there at all. We couldn't simply land on these worlds and walk around breathing the air. The atmospheres might lack oxygen, or contain toxic gases, or be at pressures that would crush or explode a human body. The gravity might be too high, compressing our organs and making movement exhausting, or too low, causing all the problems of microgravity we've discussed. The temperature ranges might exceed what human physiology can tolerate even with protective equipment. If alien life exists, its biochemistry would likely be incompatible or actively harmful to us. Alien proteins wouldn't be digestible by our enzymes. Alien microorganisms might not infect us, but could create toxic byproducts or outcompete beneficial Earth microbes in ways that undermine our health. The very soil and water might contain chemicals toxic to human biology, but harmless to native life adapted to them over billions of years. The idea of finding an Earth twin, a planet so similar to Earth that humans could thrive there naturally, is astronomically improbable. Earth itself is the product of billions of years of specific evolutionary history. Its atmosphere was created by life and is maintained by life. Its oceans, climate, magnetic field, and every other characteristic that makes it habitable are the result of unique circumstances unlikely to be replicated elsewhere. Even if we somehow overcame all the challenges of interstellar travel, we would likely arrive at worlds we could only inhabit by living in sealed habitats, essentially remaining in spacecraft that sit on a planetary surface rather than orbiting in space. At that point, what was the purpose of the journey? Why travel light years to live in a sealed habitat on another world when we could build sealed habitats in our own solar system, or even in orbital space around Earth, with far less effort and cost? The biological clock of human evolution ticks to Earth's rhythm, and no amount of technological sophistication can change the fundamental fact that we are Earth organisms, evolved for Earth, adapted to Earth, and ultimately dependent on Earth for our survival. This leads us to consider yet another fundamental paradox of spacecraft design: the backup system trap. Reliability engineering teaches us that redundancy improves system reliability. If one component fails, a backup takes over. But in spacecraft design, particularly for missions where mass is critical, redundancy becomes self-defeating in ways that make missions less rather than more reliable. Consider a critical system like oxygen generation. You might start with one oxygen generator, but it might fail, so you add a backup. That backup increases spacecraft mass, which requires more fuel, which requires more structure to hold the fuel, which increases mass further. The additional mass means more wear on other systems, higher energy requirements, and increased structural stress throughout the spacecraft. But 2 oxygen generators might not be enough. Both could fail from a common cause: radiation damage, manufacturing defect, or design flaw. So you add a third, increasing mass again. Where do you stop? With 4 backups? 5? Each additional backup improves reliability against random failures but increases overall system complexity and mass, which introduces new failure modes. The backups themselves need supporting systems. They need power connections, data connections, physical mounting, and integration with the primary systems. All of these interfaces are potential failure points. A short circuit in the backup system could damage the primary system. A sensor malfunction could cause the backup to activate inappropriately, interfering with normal operations. Backups that sit idle waiting for a failure are themselves prone to failure. Seals dry out, lubricants congeal, electronics degrade from radiation even when not operating, and when finally called upon to function, the backup might not work. Periodically testing and exercising backups helps but requires crew time, energy, and introduces where that might cause the failure the backup was meant to prevent. Some systems cannot have simple backups. Structural components like hull sections or primary load-bearing members cannot be backed up. You cannot carry a spare spacecraft hull. For these systems, you must over-engineer the primary structure, making it heavier and stronger than nominally necessary. This adds mass, which requires more fuel, which requires stronger structure, and another recursive problem. Software presents unique redundancy challenges. Running the same software on multiple computers doesn't protect against software bugs. All copies will have the same bugs. Running different software implementations that might have different bugs is expensive and introduces compatibility and coordination problems. Moreover, radiation-induced bit flips can corrupt software in subtle ways that might not be detected until they cause system malfunctions. The redundancy paradox becomes acute for highly reliable systems. If a system is already 99% reliable, adding a backup improves reliability to 99.99%, a small absolute improvement. But that backup adds perhaps 50% more mass to the subsystem. Is the marginal reliability improvement worth the mass penalty? The mathematics often says no, but then you're accepting that some critical systems will fail with 1% probability, which over a 40-year mission almost guarantees failure. Complex systems have multiple potential failure modes, and different failure modes require different backup strategies. A pump might fail mechanically, requiring a spare pump. It might fail electrically, requiring backup power systems. It might fail due to contamination, requiring filtration backups. It might fail due to software control errors, requiring software redundancy. Protecting against all failure modes multiplies the backup requirements. There's also the problem of what engineers call common mode failures. These are failures that affect both primary and backup systems simultaneously. A micrometeorite puncture might damage both a primary power cable and its backup if they are routed together. A software bug might affect multiple redundant computers running the same code. A design flaw might be present in all units of a particular component. Radiation might damage multiple systems in the same event. Protecting against common mode failures requires not just redundancy but diversity, fundamentally different approaches to solving the same problem. For example, having both solar panels and nuclear reactors for power, or both chemical and biological oxygen generation methods. But diversity dramatically increases complexity, requiring crews to maintain expertise on multiple completely different systems, requiring different spare parts inventories, and creating integration challenges between dissimilar systems. The mass penalty of redundancy interacts destructively with the rocket equation. Adding 10% more mass for redundancy doesn't just require 10% more fuel. Due to the exponential nature of the rocket equation, it might require 20 or 30% more fuel at launch, depending on mission parameters. This additional fuel has its own mass, requiring more structure, more powerful engines, and compounding throughout the entire spacecraft design. There are also diminishing returns on redundancy. The first backup provides the largest reliability improvement. The second backup provides less improvement. The third backup provides even less. But each backup costs roughly the same in terms of mass and complexity. You quickly reach a point where additional backups cost more than they benefit. Consider a specific example: the computer systems controlling life support. You might have 3 independent computers using majority voting. If one malfunctions, the other 2 outvote it. This is a well-established reliability approach. But those 3 computers require 3 times the power, 3 times the cooling, 3 times the physical space, and triple the potential points of failure in their supporting systems. They also require complex voting logic that itself might contain bugs or fail in ways that cause incorrect decisions. The voting logic faces subtle challenges. If one computer starts giving wildly incorrect values, the others can identify and ignore it. But what if one computer is subtly wrong, giving values that are plausible but incorrect? The voting logic might not detect this, and the system could make wrong decisions based on a majority vote that happens to be incorrect. You need more sophisticated error detection, which means more complex software, which means more potential bugs, which brings us back to needing more redundancy. Physical backup systems take up space, and space on a spacecraft is at a premium. Larger spacecraft require more structural mass, more whole surface area that needs to be protected and maintained, and more volume to pressurize and condition. The habitat sections can't simply be made arbitrarily large to accommodate redundant systems because every cubic meter of pressurized volume has significant mass and energy costs. Redundancy also complicates maintenance and repair. With multiple parallel systems, determining which system has failed can be difficult. Diagnostic procedures become more complex. Crew members must understand not just how each system works but how they interact. When failures occur in redundant systems, deciding which to repair first, how to allocate limited repair resources, and how to manage degraded operations becomes challenging. There's a psychological dimension too. Knowing that critical systems have multiple backups can create complacency. Crews might tolerate degraded performance, or minor failures in primary systems, thinking the backups will handle problems. This complacency can lead to situations where multiple backup systems have failed before anyone realizes the severity of the situation. The backup system trap creates an impossible optimization problem. Too little redundancy, and the mission will certainly fail when critical systems break down. Too much redundancy, and the spacecraft becomes too massive to propel to useful velocities, or so complex that the interactions between redundant systems create more failure modes than they eliminate. There's no sweet spot where you have adequate reliability without unacceptable mass penalties. This problem is especially acute for interstellar missions because the timescales are so long. For a 6-month Mars mission, you might accept lower redundancy because the probability of critical failures is manageable. For a 40-year interstellar mission, the probability of critical failures approaches certainty regardless of redundancy levels. You're not trying to prevent failures but to delay them, and eventually, delay isn't enough. The backup system trap is yet another fundamental barrier that makes long-duration space missions impractical. It's not a problem that better engineering can solve because it's intrinsic to the nature of complex systems operating in hostile environments over extended periods. You cannot engineer your way to perfect reliability, and anything less than perfect reliability eventually becomes catastrophic failure given sufficient time. All of this discussion has assumed, perhaps generously, that we could even find a suitable destination. The notion of habitable exoplanets, frequently mentioned in popular science reporting, is a profound oversimplification that borders on deception. The actual requirements for a planet to be genuinely habitable for humans are so specific and so stringent that even planets in the so-called habitable zone are almost certainly unsuitable for human life. The habitable zone is defined as the range of orbital distances from a star where liquid water could theoretically exist on a planet's surface. This is an extraordinarily crude metric that ignores hundreds of other factors essential for actual habitability. Liquid water can exist in a wide range of conditions, many of which would be instantly lethal to humans. Consider atmospheric composition. Humans require an atmosphere with approximately 20% oxygen, and the remainder mostly nitrogen, at a pressure close to Earth's 1 atmosphere. Too much oxygen, and fires burn uncontrollably and our tissues suffer oxidative damage. Too little, and we suffocate. Carbon dioxide concentrations above a few percent are toxic, causing headaches, confusion, and eventually death. The presence of toxic gases like methane, ammonia, hydrogen sulfide, or chlorine, even in small concentrations, would be lethal. The probability that an exoplanet would have this precise atmospheric composition is vanishingly small. Earth's atmosphere was created by billions of years of biological activity. Early Earth had a completely different, unbreathable atmosphere. Only after photosynthetic organisms evolved and spent billions of years releasing oxygen did Earth's atmosphere become suitable for complex life. An exoplanet without a similar biological history would have an atmosphere determined purely by its geology and chemical composition, and there's no reason to expect this would produce breathable air. Even if an exoplanet had significant oxygen, this would indicate the presence of life. Oxygen is reactive and doesn't persist in atmospheres without continuous replenishment by living organisms. But alien life would have evolved completely independently, with different biochemistry. Its proteins, carbohydrates, lipids, and other biomolecules would be structurally different from Earth life. We couldn't eat alien organisms because our digestive enzymes wouldn't break down alien biochemistry. Alien plants wouldn't provide nutrition. Alien microorganisms might not infect us directly, but could still be harmful through various mechanisms. Gravity is another critical factor. Human bodies evolved for Earth's gravity. A planet with significantly higher gravity would make movement exhausting, put dangerous stress on our cardiovascular systems, and could cause structural damage to our organs over time. A planet with significantly lower gravity would cause all the problems of microgravity we've discussed. The range of gravities humans can tolerate long-term is probably quite narrow, perhaps 0.8 to 1.2 Earth gravities. This limits potential habitable planets to those with masses very close to Earth's mass. Day length matters. Our circadian rhythms evolved for 24-hour days. Planets with much shorter days would subject us to exhausting rapid light-dark cycles that would disrupt sleep and metabolism. Planets with much longer days would create massive temperature swings between the heated day side and cold night side, and would disrupt circadian rhythms in ways that cause serious health problems. The rotation rate of a planet is determined by its formation history and has no reason to match Earth's. Axial tilt determines seasons. Earth's moderate axial tilt creates seasonal variations that, while sometimes challenging, are manageable. A planet with no axial tilt would have no seasons, creating climate zones that never change and potentially uninhabitable polar regions. A planet with extreme axial tilt would have seasons of such severity that much of the planet would alternate between being frozen and scorched, making stable habitation impossible. Magnetic fields are essential for protection from stellar radiation. Earth's magnetic field deflects most of the solar wind, protecting our atmosphere from being stripped away and protecting life from dangerous radiation. A planet without a magnetic field would be bathed in radiation from its star, making surface life impossible. Many exoplanets likely lack magnetic fields, either because they're geologically dead like Mars or because their internal structure doesn't generate one. The type of star matters immensely. Most stars are red dwarfs, smaller and cooler than our Sun. To be in the habitable zone of a red dwarf, a planet must orbit very close to the star. This creates tidal locking, where one side of the planet always faces the star and the other side is in perpetual darkness. One hemisphere would be scorchingly hot, the other frozen, with only a narrow twilight zone potentially habitable. Red dwarfs also emit more radiation in the ultraviolet and X-ray spectrum and produce powerful stellar flares that would sterilize planetary surfaces. Larger, hotter stars than our Sun burn through their fuel quickly, existing for only millions or billions of years rather than the 10 billion years our Sun will last. Complex life on Earth required billions of years to evolve. A planet around a short-lived star might not have time for complex life to emerge before the star exhausts its fuel and expands into a red giant, incinerating any planets in its habitable zone. The presence of a large moon like Earth's moon is important for stabilizing axial tilt and creating tides that may have been essential for the emergence of life. Most planets probably don't have large moons. The specific circumstances that created Earth's moon, likely a massive impact in Earth's early history, are probably rare. Plate tectonics are essential for long-term habitability. Plate tectonics recycle carbon between the atmosphere and the planet's interior, maintaining stable greenhouse gas levels over geological time. They also create geological diversity and may be essential for generating the planet's magnetic field. Many planets probably lack plate tectonics, with stagnant lid surfaces like Venus or Mars that would lead to very different long-term evolution. The presence of a Jupiter-like planet in the outer solar system may be important for protecting inner planets from asteroid and comet impacts. Jupiter's massive gravity captures or deflects many potentially dangerous objects that might otherwise impact Earth. A planetary system without such a protector might experience far more frequent catastrophic impacts. Even chemical composition at the micro level matters. Earth has specific concentrations of elements essential for life: carbon, nitrogen, phosphorus, sulfur, iron, and dozens of trace elements. A planet formed in a different part of the galaxy, from a different stellar nebula, might have very different elemental abundances. Too much of certain elements could be toxic. Too little of others could make biochemistry impossible. The history of impacts, volcanic eruptions, ice ages, and other catastrophic events has shaped Earth's biosphere in ways that can't be replicated. These events drove evolution, caused extinctions that opened ecological niches for new forms of life, and created the specific environment we inhabit. Another planet would have a completely different history, leading to completely different conditions. When you multiply all these factors together, atmospheric composition, gravity, day length, axial tilt, magnetic field, stellar type, moon presence, plate tectonics, protective giant planets, elemental composition, and geological history, the probability that any exoplanet would be genuinely habitable for humans becomes infinitesimally small. We're not just looking for a planet in the habitable zone. We're looking for an Earth twin, similar in hundreds of specific ways, and such planets are probably extraordinarily rare if they exist at all. Even if we found such a planet, we couldn't know whether it was truly habitable without visiting it. Observations from light years away can tell us approximate size, orbital distance, and perhaps basic atmospheric composition, but not the detailed characteristics we need to know. We might travel for decades toward a promising world only to discover upon arrival that it's unsuitable in ways our distant observations couldn't detect. And even if we found a genuine Earth twin, we couldn't just land and start walking around. Unknown pathogens, incompatible biochemistry, and countless other hazards would make it as dangerous as the most hostile environment on Earth. We need to live in sealed habitats, rendering the entire purpose of traveling to another world questionable. The habitable planet myth is perhaps the most seductive false promise of interstellar travel. It imagines that if we could just reach another star, we'd find worlds where humanity could thrive. The reality is that Earth is not just our home but our only home, the only planet in the universe that we can be certain is compatible with human biology. Because we evolved here and for here. Beyond all the technical and practical barriers we've discussed, there remains perhaps the most profound obstacle of all. The ethical implications of interstellar missions are so deeply troubling that pursuing them would be morally unconscionable. The ethical problems operate on multiple levels, from the individual to the civilizational, and they reveal that even if we could accomplish such missions, we shouldn't. Consider first the ethics of sending humans on one-way missions into deep space. Anyone volunteering for such a mission might provide informed consent, but can anyone truly understand what they're consenting to? Can someone sitting on Earth, surrounded by friends and family, with the full richness of planetary life around them, genuinely comprehend what decades of confinement in a small spacecraft would be like? The psychological research on choice suggests that people are remarkably bad at predicting their future emotional states, especially for experiences radically outside their current experience. Moreover, informed consent requires that people understand the risks. But for interstellar missions, many risks are unknown or poorly quantified. We don't have experience with decades-long exposure to cosmic radiation, multi-generational confinement, or arrival at exoplanets. We'd be sending people into situations where the dangers are literally uncertain, and informed consent under radical uncertainty is philosophically problematic. The time dilation problem creates additional ethical issues. People who volunteer for missions knowing they'll age slower than Earth are choosing to permanently exile themselves from everyone they've known. Is such a choice rational? Or does it represent a form of self-harm that society should not enable, similar to how we don't allow people to sell themselves into slavery even with their consent? For generation ships, the ethical problems multiply catastrophically. The initial crew might consent to the mission, but their children don't consent to being born in space. Their grandchildren don't consent to spending their entire lives maintaining a spacecraft toward a destination they've never seen and have no personal connection to. These future generations are condemned to imprisonment without having committed any crime, without any choice in the matter, because their ancestors made a decision decades or centuries before they were born. Creating people who will never experience planetary life, who will spend their existence in sealed environments maintaining machinery, who have no possibility of leaving or choosing different lives, seems like a profound moral wrong. It's condemning human beings to lives of severe limitation for a goal they didn't choose and may not value. The fact that they don't yet exist doesn't eliminate the ethical problem. We still have obligations to future people we create, including the obligation not to create them into situations of suffering or severe deprivation. There's also the question of what message such missions send about human values. Spending enormous resources on quixotic interstellar missions while people on Earth suffer from poverty, disease, and environmental degradation reveals a troubling set of priorities. The resources required for even attempting interstellar travel, trillions of dollars, the labor of thousands of people over decades, enormous energy expenditures, could instead address pressing problems affecting billions of people living today. The opportunity cost of interstellar missions is staggering. The same resources could fund medical research, education, poverty alleviation, renewable energy development, ecosystem restoration, and countless other efforts that would reduce suffering and improve lives on Earth. Choosing instead to pursue missions that are almost certainly doomed to failure represents a profound misallocation of resources motivated more by romantic fantasy than rational analysis of how to maximize human flourishing. Some argue that interstellar missions represent insurance for humanity, spreading our species to multiple worlds to ensure survival if catastrophe destroys Earth. But this argument fails on multiple levels. First, we've established that interstellar missions are essentially impossible with any foreseeable technology. Second, even if they were possible, establishing self-sustaining colonies on other worlds is even more challenging than reaching them. Third, the timescales involved mean that even if we sent missions tomorrow, they wouldn't arrive for centuries, by which time any Earth catastrophe would long since have played out. More fundamentally, the insurance argument puts the cart before the horse. If we're capable of maintaining human life on other worlds with their hostile environments, we're certainly capable of maintaining human life on Earth even after severe catastrophes. Earth, even after nuclear war, asteroid impact, or climate change, would remain far more hospitable than any exoplanet. Our resources would be better spent preventing catastrophes and building resilience on Earth rather than pursuing impossible interstellar missions. There's an element of escapism in interstellar mission enthusiasm that's ethically troubling. Rather than confronting the difficult work of making sustainable civilization on Earth, some prefer to fantasize about leaving Earth behind and starting fresh elsewhere. But we would bring our problems with us. Human nature doesn't change because we're in a different location. If we cannot create sustainable, just, peaceful civilization on Earth with all its resources and beauty, what makes us think we could do so in the harsh environment of space or an alien world? The ethics of first contact with alien life, should it exist, are also deeply problematic. Human history shows that contact between technologically disparate civilizations typically ends badly for the less advanced civilization. Even if we intend no harm, our mere presence could be catastrophic for alien ecosystems or civilizations. Do we have the right to potentially contaminate or disrupt alien worlds simply to satisfy our curiosity or desire for expansion? The risk of contamination works both ways. Bringing alien microorganisms back to Earth, even inadvertently, could introduce pathogens or invasive organisms that wreak havoc on Earth's biosphere. The same sealed environment protocols that make it difficult to sustain human life would make it nearly impossible to prevent contamination. Is the potential gain worth this existential risk to Earth's biosphere? There's also a hubris in assuming humanity's destiny is to spread across the stars. This narrative, common in science fiction and popular science, frames Earth as merely a cradle that humanity must eventually leave. But perhaps Earth is not just our cradle but our proper home, and our destiny is not conquest of space but stewardship of our planet. Perhaps maturity as a civilization means accepting our place rather than constantly seeking to transcend our limitations. The resources and human effort that might be directed toward impossible interstellar missions represent a tragic waste when redirected from problems we can actually solve. Climate change, biodiversity loss, pandemic disease, poverty, inequality. These are challenges we have the knowledge and resources to address if we choose to prioritize them. Every dollar and every human hour spent on interstellar mission fantasies is diverted from these solvable problems affecting billions of people. Moreover, the focus on space colonization can provide a dangerous psychological escape valve, allowing people to avoid confronting terrestrial problems. If we believe we can always leave Earth behind and start over elsewhere, we may feel less urgency about preserving Earth's habitability. This kind of thinking is not just impractical but actively harmful, creating moral hazard that excuses environmental destruction and social failure. The ethical calculus overwhelmingly points toward focusing our attention, resources, and ambitions on Earth. This is not a counsel of despair but of realism and responsibility. We have one known habitable planet, one place where human flourishing is possible, and that planet needs our care and attention. Pursuing impossible dreams of interstellar travel while neglecting our actual home is not visionary. It's irresponsible escapism that abandons our ethical obligations to present and future generations who will inherit the Earth we leave them. In the end, after examining every dimension of the problem, the distances, the physics, the engineering, the biology, the psychology, the ethics, we must confront a conclusion that might seem pessimistic but is actually liberating. Humanity's place is in our own solar system, primarily on Earth. And this is not a limitation to overcome but a reality to accept and embrace. The dream of visiting other star systems is understandable. It speaks to deep human impulses, curiosity about the unknown, desire to explore, hope for new beginnings, and the romantic notion that we're meant for something grander than life on a single world. These impulses have driven human achievement throughout history, pushing us to cross oceans, climb mountains, and eventually reach into space. But there's a profound difference between difficult achievements and impossible ones, between challenges that require ingenuity and determination versus barriers that are written into the fundamental laws of physics. Crossing an ocean is difficult, traveling faster than light is impossible. Climbing a mountain is challenging, living without Earth's gravity, atmosphere, and biosphere indefinitely is impossible for creatures evolved for Earth. We must learn to distinguish between these categories. Understanding and accepting these limits doesn't diminish human achievement. The Apollo program, which put humans on the moon, represents one of humanity's greatest accomplishments. The robotic missions that have visited every planet in our solar system, that have landed on comets and asteroids, that have sent back images from the surface of Mars and the clouds of Jupiter, these are triumphs of human ingenuity and determination. The International Space Station, the James Webb Space Telescope, and countless other space endeavors demonstrate what we can accomplish within the bounds of physical law. Our solar system offers vast opportunities for exploration and scientific discovery. Mars, despite being cold and airless, is far more accessible than any exoplanet. The moons of Jupiter and Saturn, Europa, Enceladus, Titan, may harbor subsurface oceans or exotic chemistry worth studying. The asteroid belt contains resources that might someday support space industry. The outer solar system holds countless mysteries waiting to be explored. More importantly, Earth itself remains largely unexplored in significant ways. We know more about the surface of Mars than about the deep oceans of our own planet. We're still discovering new species regularly. We don't fully understand Earth's climate system, its ecosystems, or the complex interactions that maintain habitability. Directing our curiosity and resources toward understanding and preserving Earth would yield far greater returns than pursuing impossible interstellar missions. The universe reveals itself to us not primarily through physical travel but through observation and understanding. Telescopes, both ground-based and space-based, bring distant galaxies within our intellectual reach even if they remain physically unreachable. Radio telescopes listen for signals from across the cosmos. Particle accelerators probe the fundamental nature of matter and energy. Mathematics and physics allow us to understand the universe's structure and evolution without visiting every location. This approach to exploring the universe, through observation, theory, and intellectual rather than physical conquest, is not a second-best option but perhaps the most appropriate response to a cosmos so vast. The universe teaches us humility. Its scale dwarfs our ambitions. Its laws constrain our actions. Its age makes our civilizations seem like mayflies. Perhaps the proper response to this reality is not to rage against our limitations but to accept them with grace while maximizing what we can accomplish within those bounds. There's profound beauty in Earth's uniqueness. Out of all the planets we've discovered, all the worlds we know to exist, Earth stands alone as a place where creatures like us can thrive. This doesn't make us cosmically insignificant, it makes Earth cosmically precious. We are the universe's way of knowing itself, and that knowledge originates from and perhaps must remain rooted in this particular pale blue dot. Our destiny may not be to physically conquer the stars but to understand them. To observe, to theorize, to discover the laws that govern reality, to create art and music and literature that express our response to the cosmos, to build a civilization that can persist and flourish on Earth for millions of years. This is not a small or disappointing destiny. It's the only destiny available to us, and it's more than enough. The resources currently devoted to fantasies of interstellar colonization would be better spent on making Earth's civilization sustainable, just, and beautiful. Solving climate change, preserving biodiversity, eliminating poverty and disease, creating art and culture, pursuing fundamental science. These are achievable goals that would improve billions of lives. They represent our actual frontier, the real challenges we're equipped to address. Accepting that we'll never reach other planets beyond our solar system doesn't mean abandoning curiosity or exploration. It means channeling those impulses toward what's actually possible. Robotic exploration of our solar system, increasingly sophisticated telescopic observations of the universe, fundamental research into physics and biology, and most importantly, learning to live sustainably and well on Earth. These pursuits can occupy humanity for millennia. We are Earth's consciousness, Earth's way of understanding itself and the universe it inhabits. This role doesn't require us to leave Earth permanently or to spread across the galaxy. It requires us to observe, to think, to understand, and to appreciate. The universe is vast and we are small, but small things can understand vast things, and in that understanding find meaning and purpose. The tyranny of distance, the rocket equation, the speed of light, the energy requirements, the radiation, the impacts, the life support challenges, the psychological impossibilities, the time dilation paradox, the generation ship problems, the deceleration barrier, the communication void, the entropy of systems, the gravity requirement, the biological incompatibility, the backup system trap, the absence of habitable worlds, and the ethical unconscionability. Each of these alone would be a severe challenge. Together they form an impenetrable wall of physical law that forecloses interstellar travel as a realistic possibility for humanity. This is not a temporary situation awaiting better technology. These barriers are fundamental features of the universe we inhabit. A civilization 1,000,000 years more advanced than ours would face the same constraints because they arise from the structure of spacetime itself, from thermodynamics, from the finite speed of causality, and from the biological nature of life evolved for one specific world. Recognizing these limits is not defeatism but wisdom. It allows us to direct our finite resources and efforts toward what's actually achievable rather than wasting them on impossible dreams. It helps us appreciate Earth's uniqueness and preciousness. It reminds us that our responsibilities lie here, with this planet and its inhabitants, not in fantasies of escape or expansion into an unreachable cosmos. We are not going to other planets beyond our solar system. We never will. This is not because we lack courage or vision or determination, but because the universe's laws forbid it. And that's okay. Earth is enough. Understanding the universe from our home is enough. Building a flourishing civilization here is enough. We don't need the stars. We have our sun. We don't need 1,000 worlds. We have the one world that can sustain us. This is not a limitation but a liberation, freedom from impossible fantasies to focus on actual possibilities, on the real work of creating and maintaining human civilization in the only place in the known universe where it can exist. The cosmos will remain forever beyond our physical reach, but never beyond our intellectual grasp. That is humanity's true gift and purpose, not to conquer space, but to understand it, and in understanding it, to understand ourselves and our proper place in the grand scheme of existence. We are bound to Earth not by failure but by the fundamental nature of reality, and recognizing this truth is the first step toward accepting our role as stewards and students of this miraculous, irreplaceable world we call home. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.